module 1. We are now going to move on to module 2. Okay, so module 2 is where most of the questions will come out from. We have to spend a bit more time here, right? So if everybody's all right, we will continue on with module 2, chapter 1. Let's see if everybody's back. All right. So module 2, chapter 1 will be intelligent storage components. So this chapter describes the component of storage systems, including the controller enclosure, disk enclosure, interface modules, and connection modes between the enclosures and their respective working principles. Upon completion of this topic, you will be able to better understand the storage product forms, understand the functions and components of controller enclosures and disk enclosures, understand the working principles of basically hard disk drives and solid state disks, cables and interface modules for connecting storage enclosures, and the connection methods. Objective-wise, we have 5 things to go through. So we'll go through a controller enclosure, then we'll talk about a disk enclosure, then we'll talk about the expansion module, the disks, and the interface modules themselves. So the storage product form. First, we have to understand there are 2 different types of storage product forms. First, we call integration controller. Integration controller, yeah. And the other one will be separation controller. So these are the 2 basic storage product forms. Basically, the integration controller, meaning that the controller is integrated with disks. So you can see disks here, and behind the disks will be the controller module. So this will be the front, this will be the back. So this is the front end, this is the back end. The separation controller, the disk modules and the storage controller are separate. So basically, the controller module won't have disks. You have to attach it to another disk array. So by default, the controller won't come with disks, right? In some sense, these are, well, easier said. In some sense, these are cheaper, and these are the more expensive products. So the expensive product, meaning this will be the performance-based guys, right? The separation controllers. Then, of course, you have the integrated bay products, which is basically, you're basically buying a whole cabinet of products in some sense. This will be like Fusion Cube or something like that. Okay, so let's look at the product one by one. So here we are using OceanStor Dorado V6, right? Okay, so usually I don't like to show it here because here, yeah, you just see picture forms, not so cool. If you can go to this document, you'll find something called support.it.huawei.com/storage/hashtag/home. Just copy paste the guy, put it into your browser. I'll put it in the chat. So I'll just put it in the chat there for everyone. So you can copy paste that into a browser. You can open up Huawei's 3D storage product. It will take some time, but don't worry. Anyways, before we continue, how is the COVID situation in Indonesia, man?
Still not good.
Not good. How are the numbers every day? I mean, like how many new people infected and all this stuff? Like Malaysia is going up again.
Oh, I don't know exactly, but we're still
About
in
5,000.
quarantine.
5,000, right?
5,000.
5,000. Oh, It's coming, see, Malaysia is coming the same. Now we are back to 4,000 per day. And I thought can go back to work, man. Doesn't look like it. Yeah, another thing. Do you guys enjoy working from home or working in the office?
Enjoy at home.
Really? You can do work from home, sir? I cannot work from home, man. Yes, sir. But you're okay working from home, sir? That's cool. That's cool. I just wanted to know if you guys enjoy working from home or working in office. I would say at some point, I'd rather go to the office and work, man. At home, you got so many distractions.
You're right.
For some reason, this is taking a long time. So, see if this works again. So usually they'll always have some issues here. Let's double check that. Maybe you can directly go to Huawei.com. Products, technical support, room, tools. Let's see. Yeah, 3D experience. It's the same place, right? Some reason it's slow today. Usually it's quite fast. All right, finally loading up. Maybe you can use this link. I think this is a better one. Unless they change something. Oh man, they always change something. Okay, so you can see here, this will be the storage 3D experience center, which is actually a very underutilized product, right? It's something that Huawei created. So like say we are using Ocean Store Dorado V6. Okay, Ocean Store Dorado V6. You'll see the base integrated controller. So let's just take a SAS module. And then I will take Ocean Store Dorado. So hopefully not a lot of people are using it. Yeah, expansion modules. Okay, so let that load. So these screens, you get to see the 3D model. So at least you get to see something else. So maybe you guys can get it faster. For me, it's somewhat slow. But once it opens up, you will get to see the 3D modules and you get to play around with those modules. So that's quite cool. Even when you do classes or it's actually meant for like sales and marketing and stuff. But yeah. So today just super slow for some reason. Maybe my connection is quite bad. I don't know. Am I breaking up or anything? No, right? So taking a while, slowly loading up. All right. Anyways, I'll let them load. We'll go back to our PowerPoint slide first. So that 3D center basically will show you the 3D product, how it actually looks like. Rather than seeing it just from a slide, you can actually move around the product and turn it around, play around with it. So quite cool. So first we talk about storage enclosures. So the storage enclosure here they are talking about an integrated module. So this is an integrated storage controller, right? So integrated simply means you will have your basically your management module, your disk interfaces, right? And so this is separation module, right? So you'll have your interface module, so your basically where your interface is connected to the controller module, your power module, your management module, your system subtract is basically just a casing, and the actual controller itself. You'll see here Huawei separation modules usually come with 4 controllers, right, by default. So basically you have 4 storage controllers for one module. If we could see it in the Huawei storage 3D, yeah, slowly coming up. Some reason, super slow. Maybe we do another. This is the thing I don't like. Half the time got problems, man. Maybe take a lower scale product. Push install V3. See if we can do something with a V3 product. Somehow it's not loading in. So yeah, something wrong with the website, man. Always have these issues. For some reason, it's half the controller. Let's see if I can do an explosion. Yeah, it's not loaded yet. Let it load. It will slowly load some stuff. Right? Anyways, we'll continue on. So the controller module basically, for the separation module itself, is just the controller alone. So there will be no disks. There will be no basically any storage itself. It's just the controller. If you add on top of the controller, you have to buy like extra disk arrays. So for this kind of separation module, you will have to buy disk arrays, right? So it doesn't work with the controller itself. This is how a separation module looks like. If you can open up the screen, and then you can see later on, it will be much more nicer to see, okay? So front end view of a controller enclosure. So if you're talking about an integrated controller enclosure, this is how it look like. So integrated controller enclosure, you will have your disks. So all these are actual storage disks. By default, Huawei uses 2.5-inch disks. You can, however, take it to 3.5-inch for your hybrid controllers. If you're using OceanStaw Dorado, by default, there's no 3.5. It's only 2.5, right? If you're using OceanStaw Dorado. Because why? OceanStaw Dorado is an all-flash controller. All-flash simply means it only can use SSDs, okay? So the controller enclosure in the front, you will have, of course, the icon, which indicates the controller enclosure ID that will be up here. Okay, so that's this guy. Then you'll have the location indicator, which is actually quite a good, what do you call this? Quite a valuable thing in some sense, whereby because all the controllers and the disk enclosures kind of look the same, if you buy everything Huawei product, they will look like this, right? So you want to find the location of something. So you'll remote login into the controller enclosure. So remote login. So just say you're a user, you remote login into controller enclosure, and then you say something is wrong with this disk, right? But if you go into your server room, how do you want to find the controller, right? Because in your server room, you might have multiple racks and all these things. And then you have multiple devices, right? So this might be a Cisco switch. This might be like a Huawei router. This might be storage controller 1, storage controller 2, so many things. So with the location indicator icon, you can remote login into the controller, activate the enclosure location indicator. This guy will start blinking. right? So this guy will start blinking, and you can just leave it blinking. So when you go inside the server room, you can see one blinking light on the controller, and you can locate the controller. This is for physical location. So maybe if you send like an engineer to site, you are off site. So you talk to the engineer and say, okay, go to the controller or go to the server room, check rack 2, you will see a blinking blue light, right? Something that is blinking blue light. You will show him how the blinking blue light looks like. And then when he goes to the server room, you'll see this blinking, and then you can find or locate the controller itself. And then you'll have the controller alarm. So if anything goes on, the alarm icon will straight away start appearing. Maybe this disk is failing, or maybe the RAID group is not working properly or something like that. The alarm icon will generally be there. And finally, of course, you have the power icon, right? So the power icon indicates whether the controller is up or down. That's it, okay? And this is both the situation for integrated controllers and separation controllers. So integration controllers and separation controllers, they will have the same icon. So Huawei keeps it a bit similar. These are both Ocean Store Dorado. So they look similar. Even if you look at the older Huawei products, they actually look same, right? It's just that internally they are different. So let's see if our guy came up again. All right, finally it's up. Okay. So this is a Huawei Ocean Store, man. Take the big guy. Yeah, why not? Let the guy load. So this is a Huawei Ocean Store 3000 V6 SAS edition. So if I do an explosion, you can see here. Okay. So if you move up here, you can see on the left here. So let me do some stuff. So on the left here, these are all your displays, right? So what are you clicking right now? So currently I'm clicking on the system subtrack, I think, right? You can see here. Then here you have your front panel, which is just basically a panel. Then you have your disk module. So these are all disks. And if you scroll in, you can see what kind of disks are they. So these are SAS 15 terabyte 10K disks, 2.5 inch. Okay. And then if you move the air baffle, yeah, basically that's just a cover. Heatsink, right? These guys. You'll find the heatsink here, heatsink here. So let me just move the components themselves. Move this guy out. You can actually delete this guy. Baffle. So these are the heatsinks, right? This guy and this guy. So both heatsinks, right? So if you look at them, this is how they look like in general. Oh, okay, my bad. Put them back there. Then you have the actual controller itself. So this is for two double controller, dual controller action, right? So original view, do an explosion again, move out the components. Oh, this is the casing for the battery, power module. Okay, controllers. This is the controller enclosure, Okay. So these are the actual controllers. This is why the storage system is expensive. These guys are basically the price of the storage system, right? So these are the controllers. Then you have the fans, of course. So where are the fans? Here. We move at the front. Okay, move out the air baffle. All these guys are the fans. Okay. So you can see for two controllers, you have 8 units of fan systems. I'll move the disk back. That. Okay, 1, 2, 3, 4, 8. So 8 fan systems. Then you have your backup battery units. Your backup battery units, I have removed the guys, but yeah, these are your backup battery units. So if you remove them, so maybe we can remove whatever we saw. Remove the system subtract, front panel, disk module, air baffles, heat sinks, controllers themselves, then the fans. Now you're only left with the power module, the front end and back end IO port, and the casing for the power modules, right? So that are all things you'll find in an integrated controller. So if you look at it originally, this is how it looks like, and you can see everything has a green button, so you can go inside and basically see everything, right? So if you do an explosion, what is this? They will tell you everything in demand, right? Okay, so like what port is this? This is a serial port, so maintenance network port, management port 1, front-end I/O modules, onboard Gigabyte ports, onboard 12 gigabyte, right? Power modules, controller modules, CPU, heatsink. So this is how you basically run around and play with the controller. It's very, very useful to have this kind of 3D view, because if you don't have the 3D view, then yeah. So this is integrated controller module, whereby it's integrated with disks. So you have your disks and all this stuff. Okay, so you can calculate how many disks they have. Basically, they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 22, 23, 24, 25. Okay, so keep that in mind. They will definitely ask you the question, if possible, how many disks in a 2.5-inch controller enclosure? 25 disks for 2.5. For 3.5-inch disk, you have 3, 3, 3. So you can have about 9 disks, 9 or 12 disks for 3.5-inch disks. But for Ocean Star Dorado, they only support 2.5-inch and 1.8-inch NVMe. So you can see by NVMe disk enclosure. So Smart 100, okay. Yeah, NVMe disk enclosure. Okay. So you'll see how the disk enclosure looks like later on. And this is the integration module. Okay. You want to play around with it, go ahead. Just use the component mode, move out each component and stuff. Will be better understanding. I suggest you do that so you understand how the controller, basically what are the key components or key hardware modules inside the controller itself. Okay. Then we look at the Ocean Star Dorado 8000 V6 NVMe. So this is a separation controller. If you do an explosion, oh man, everything is white. Oh man, thought everything is okay already. Oh well, should be loading. But anyways, if you do an explosion, you should see 4 controller modules, right? So it's slowly loading up. So just using this product, it's much more easier to see. Of course, now it's lagging a bit. But generally, you will have 4 controllers. So these will be controller boards, 1, 2, 3, 4. And you'll see there is no disks involved. So you remove the air baffles, you remove the system subtract, and also the heatsink, let's say, and the controllers. Basically, it's only full of controllers, fan modules, front panel you can remove, backup battery units, which are these guys here, you can see. Okay. Sorry, backup battery units are here, these guys. The power module, the fan module, everything here. Okay. This guy. Okay, backup battery units, power modules, management module, front-end I/O ports, back-end I/O ports. So what are the difference between front-end I/O and back-end I/O? Front-end I/O is basically storage to server communication. So these are the ports used for storage to server communication. Back-end I/O ports are what you call expansion modules, basically connecting your storage to disk arrays. Okay, so this is where you add you add more components. So let's say at the front-end modules, so maybe you'll have a connection here connecting to a server, right? For the back-end I/O module, so this guy, and this guy, Basically here you will connect to a disk array, right? So front-end IO, back-end IO modules, depending. You can also use the front-end IO modules to connect to a different controller. So a second controller, and so forth, right? But this is built for maximum performance. You will not find these guys built for just purely like normal environments. This will be your big guys, right? Very, very powerful. You can also see they have similarly the same stuff. So you have your location indicator here, your alarm icon, your power button, and your display ID. This controller enclosure ID is very, very important because they use something called SCSI IDs. To run SCSI, you need to know the ID itself. Okay, make sense? Cool. So this is how it looks like. So I would suggest, yes, once again, do the explosion, do the controller mode, move and bring and move stuff, right? Let's try to break some stuff. Here, what is this? So like these are the fans. And remove all, there's a lot of fans, so yeah. Then what is this? Like this is the controller enclosure itself. So if you actually want to look at the controller enclosure, you can just move it out. So move out everything. Just want to see the controller, right? So how the controller actually looks like. This is just a subtract. Remove that, remove that, remove that. And this is your controller, right? So you have your CPU there. You can move all your CPU sets. Then you'll have your actual motherboards, your memory cards, right? All this stuff. Make sense?
Question, sir.
Yeah, go ahead.
About the 18 series, 8000 series, 3000 and so on. What's the difference? It's just more storage, more hard disks?
No. So like this guy will be the entry level. So 3000 will be the lowest level. This guy will have certain, let's say, features. Dorado 5000 will be the more higher level, so what we call the mid-range. V6 is also, 6000 is also mid-range, and this will be the high-end guys.
So that's different about the controller? Different
cache size, different processing power.
Okay. How about the V3, V5, V6?
V3, V5, V6, okay. So you'll have all flash storage. So all flash storage, you have Ocean Store, Dorado V3 and V6. And you have all flash Ocean Store F. So anything with F at the back will be flash, except for Dorado. Dorado by default is all flash storage, right? Ocean Store F is the flash storage, right? So you have a lot of different types of Ocean Store stuff. Hybrid flash storage will be the Ocean Store V5 and V3, right? So V5 and V3 is the basic hybrid storage products. What I mean by hybrid storage products, let me just show you. Okay. Hopefully they open up. Man. Oh, this one I need to open up also. So the Dorado guys, by default, all flash, SSDs only. You cannot do anything else. You cannot add a SAS disk or SATA disk. Same with all flash storage. So if you see anything with an F at the back, right? So Ocean Store F, that is flash storage. Only SSDs. Hybrid storage product can contain SSDs and HDDs. So basically, you can add solid state disks and hard disks. Does that make sense, sir?
Okay.
But there are a lot of different versions and all that. I don't recommend that you remember all the series. just take note of what can be like V5, V6, and all this stuff, and understand the characteristics of like all flash storage, hybrid flash storage, and stuff. But if you want to remember all the different products, usually they start for OceanStor V3 is 2006, 2008, 5003. Then you'll have 55, 56, 58, 68, 18, 500, 18. So yeah, V5 the same thing, but V5 you'll have OceanStor 2800. Then they jump to 5 series product. This will be your mid-range, and your high-end products will be your OceanStor 1800 and OceanStor 6800. The Kunpeng guy is basically a chipset built by Huawei. So Kunpeng is an ARM chipset. It's not x86. So if you're using like Intel-based clients and all that, if you use Kunpeng, they cannot connect, right? If you want to use x86 chipset, you have to use OceanStor V3 or just V5. Dorado products are the same, right? Make sense?
Excuse me, sir. I mean, there are OceanStor 3000 V3 and 3000 V8.
Okay, so you have OceanStor V8, you don't have.
Dorado?
V5, yes.
Yeah, we have same version, but the last we get another V3 and V5.
Yeah. So V3 is the old product. V5 is the new generation.
Okay.
Yeah. So same for Dorado. V3 is the older generation. V6 is the newer generation.
Okay. So the hardware is the same.
Hardware for V3 to V6, they have basically increased the hardware power and all that stuff. V3 will be the bit slower version, the older one. V6 will be the generally more powerful, newer one.
Okay. Thank you.
No worries. So, man, they still don't load. Okay. Let's see the load. But yeah. So, do check out these storage products, man. The best way to learn the storage is to go and see them yourselves. You can see the difference between integrated and separation, right? Separation, no disks at all. Integrated, you have disks, right? And then if you can open up the disk arrays. So maybe just close this guy. Okay. Yeah, super long, man. Oh, definitely. So InfoSight, LMS, there will be on the last day when I do the evaluation and stuff. I'll definitely give you guys entry into the TGT, right? For exam preparations. No worries, man, no worries. I want you to pass the exam as much as everybody else does, man. No issues there. Okay. So this is a high density disk. So this is actually skipping certain topics already. But yeah, for some reason it's not loading. Let the disks load. And this product can close. So loading disk by disk. So when we reach that topic, yeah, hopefully it'll be loaded by then. Okay. So there are controller enclosures, both separation and integration controller enclosure, right? No issues there. This example, they are using OceanStor Dorado V6, the latest one. The rear view of the controller we have seen. So you have your management port, which is here. Okay. You'll have two management ports. You'll have your maintenance port. Why do you have two management ports? Basically, this is for controller A, and this will be for controller B. Right? So don't take this line here. Okay. So controller A and controller B management, as long as you enter one of these guys, so it doesn't matter if you put a cable here or put your cable here, you can enter the management system for both controllers, right? Because they are basically connected to each other. So that's the management port. Then you have the maintenance port, these guys. Serial port, if you want to connect serial cables, maybe you want to do a HA or something like that. Interface modules. So here they have a bunch of interface modules. We're talking about backup battery units and power. Both are integrated inside here. SAS expansion module. So you want to do expansion to disk arrays, it's here. And yeah, that's how it looks like. The only difference is basically, yeah, for the separation controllers, the modules will just in a bit of a different, yeah.
Sorry for interrupting.
No worries, no worries.
What the difference between controller A and B? It is for redundancy, or is there any reason?
Okay, so if we go back to this picture here, right? So we go back to the Huawei 3D storage guide. You'll see that the integration module comes with two controllers. So basically you're buying one controller enclosure with two separate controllers. So they can run HA by themselves. This is why controllers are storage controllers are very expensive in some sense, because you have twice the power. Okay, make sense?
Okay,
so you're buying,
they work so redundancy. Is it for redundancy or for something?
It is for redundancy in most sense.
For redundancy, okay, thank you.
Also increasing performance, but yeah, and load balancing.
Oh, load balancing. Okay, okay, okay.
Yes, Mr.
Yep, go ahead.
How about the advantage of Huawei product from other product?
Sorry?
How about the advantage of Huawei products from other products?
That is mostly on the software side. But if you see in terms of performance, I actually have another website here for performance. We can go, this is a, what do you call this, a non-profit organization. It's called Storage Performance Council. It's a worldwide organization. Okay, so you can go to this guy and see in terms of performance. So if you want to compare performance of Huawei product, don't say price, don't check the price yet, but you want to compare performance, Huawei is actually number one in the world currently.
Very expect.
Didn't expect, right? I mean, no, a lot of people don't know this, but Huawei is actually number one in terms of performance in storage.
Thank you, sir.
No worries, no worries. So you can compare like this guy is from Mac. You can see Huawei actually dominates the storage market. You have number 10, number 9, number 8, number 7, number 5, and number 1. All Huawei products.
Which country this product distributed?
Distributed, they are distributed to all countries, sir. So you can get this product. Sorry?
American?
You're talking about the Huawei, or are you talking about this Performance Council?
Okay, okay.
Oh, the Performance Council is actually in, I think it's in Europe. These guys are called European guys.
Oh, yes.
They have people in Europe, they have people in Asia and all this stuff. But they just, well, basically Huawei will submit their storage device to them. They will do the test and see the performance and all this stuff and then put it online, right? But if you check by price, yeah.
Thank you, sir.
No issues. No. Price, yeah, you will not see Huawei in the top 10 then. Huawei is generally a bit expensive.
Okay, okay.
No issues, no issues. All right, so let that guy look.
All right.
So yeah, Huawei is not cheap, but very powerful. Okay. So this is the rear view of the controller enclosure, both separation and integrated. So this will be integrated controller. This will be the separation controller. So controller itself, you'll find everything inside Huawei. Any controller that you have on Huawei is redundant, right? Always redundant. So the base integration controller will have two controllers by default. They are connected to each other, front end and back end. So even if one controller fails, the other controller can take over, right? For the separation controllers, you'll have, I think the next picture is separation one, right? Okay. For separation controllers, if you go and check out the 3D one, you have 4 controllers. Basically means you can have up to 3 controller failures. So all these 3 guys, so let's just move these guys. So all these guys can fail. And yeah. So all these guys can fail and just leave one controller running and it still will work. It's built redundant that way. Okay, very, very powerful stuff. That's why, yeah, 4 controller enclosure, very, very powerful. 2 controller enclosure, however, if you have this guy, one controller can fail, but you can have expansion to another controller enclosure. The other controller enclosure can have another 2 controllers. So then you have much more redundancy. So this guy can fail, this guy can fail, and you still can keep running. Quite powerful stuff. Everything inside the controller enclosure is redundant. Backup battery units, back-end ports, front-end ports. If this front-end port fails, you can connect to this front-end port. If this back-end port fails, the SSDs can still connect to this back-end port. Everything redundant. Even power modules, you'll have, like usually you'll have 2 power modules. If one power module fails, the other power module can still supply power to both the controllers. Of course, in a less performance manner, there will be some performance hits. If something fails, something will be slower, but it still can work. While you're trying to fix the problem, it still can work. And most of these are all hot swappable. So if the power enclosure fails or the power device fails, power module fails, you can just take out the power module, swap in a new one while the system is running. Everything hot swappable. Of course, best practices, you should bring down the storage controller, plug and play and all this stuff, but everything is hot swappable. Disk fails, if you have a disk fail, you can take out the disk, plug in a new disk, and run the array again. No problem, right? Everything in redundant itself. And how the controller also works, you'll have basically your disks. So you'll have some disks and all that, and you'll have something called a Coffer Disk. A Coffer Disk will basically save all your information data, your configuration data and all that stuff. So if you look at this kind of picture, we go back to this guy, original view, or explosion, right? So one of these disks might be your Coffer Discs. So you can arrange one of these disks to be your Coffer Disk and stuff, right? So usually we'll use the front 2 disks as Coffer Discs, or this disk as Coffer Discs. So all the information will be saved into this disk. So anything happens, you still have your configuration on both these disks. Quite cool stuff. And that's how the Coffer Disk works, right? Backup battery unit and fan modules. Backup battery units, fan modules, everything hot swappable. So you can just remove the module, swap it back again. So you have the BBU latch. If something goes wrong with the backup battery unit, just remove the latch, pull it out, and then you can swap in a new backup battery unit. Same for the fan modules and same for the power modules at the back. Okay. Coffer disks. So usually you will set up which Coffer disk you want. All the disks will look the same, but you have to put your stickers here. So generally you will do something like this. So with the disk here, you'll go inside, you will rename this guy. So probably you'll rename this guy. You'll put some name here, Coffer disk or something. This guy also Coffer. So you will set your Coffer disk. Of course, you just put take out a nameplate tag and just put it there, right? So you identify which is your Coffer disk and stuff. Then you'll know all these other disks are basically for storage. These 2 guys will be for Coffer disk and stuff, right? This is something you do manually, of course, when you start bringing out when you initially set up the storage and stuff. So 2.5-inch copper disk, you'll have, of course, your alarm indicator, running indicator. That will be on the disk itself, on the latch, the handle, and the label, and the disk. The handle will actually come with the Huawei storage product. So if you can see properly, the disk here, basically this is the handle, right? This whole part here is the handle.
Praveen, what happened if the two disks of the copper disk have a problem?
Then you have to swap out the copper disk. So as long as the system is still running, it's okay. But if the system goes offline, then you have problem. Then you cannot save copper disk data. So if something is wrong with the copper disk, we generally straight away go and change the copper disk. Because copper disks are only used if something goes wrong with the system, right? So something goes wrong, a system shuts down and all that, they will save the data into the copper disk. If the system is still running and there's a problem with the copper disk, straight away get an engineer, send him on site, change the copper disks. Right?
So we just replace the two disks for the copper disk?
Yeah. Of course, there'll be some configuration, but...
Okay, it's hot swap, right?
Oh.
Hello?
Yeah, hot swappable.
Okay.
So here you have your 2.5-inch copper disk or your palm size 1.8-inch NVMe copper disks. Up to you. They're generally more expensive, these guys, but yeah, if you want to use NVMe, if you have the currency to do so, go ahead. Right? So this is Ocean Store Dorado. They work both for 2.5-inch and NVMe. But if you're using the NVMe module, you'll have to buy the Dorado NVMe. If you're using the 2.5-inch SAS connectors, then you'll use the 2.5-inch SAS connector. Generally much more cheaper. Okay. Power modules. Power modules are also hot swappable. If anything goes wrong with the power module, basically swap it back. Take out the power module, swap it back, right? No problems there. Right, so that is controller enclosure. Any questions? Cool. No worries. Now we move on to disk enclosures.
Praveen, I'm sorry.
Yeah,
Okay. Actually, in my institution, we already have some product from HPE and IBM and NetApp, actually. But what we are facing right now is some part of my storage is end of lifetime.
Okay.
So sometimes we have a problem how to buy some parts that already end of sales. How about Huawei? I want to know how long the lifetime of the part. If we let's say we buy this year, how long our part will be supported by Huawei?
Generally, Huawei products for storage is 10 years.
10 years.
10 years.
10 years starting from the production or from the product launching?
From the product launch.
From the product launch.
Yeah.
10 years.
10 years.
They guarantee for the part.
They guarantee for the. After 10 years, if they call end of life, then yeah. That's why Ocean Store V3, right? Right. Sorry. Go ahead.
Yeah, because I have several parts in my institution, like NetApp. We have a NetApp Fast 2020, and we have a problem with the power supply, and one of the parties have a goes wrong, and we cannot buy the part right now because end of time. So that's why that we are worried about the part, because we know that the series or it's become changed from V3 to V6, or maybe in the future will be changed to V9. We don't know.
That happens. We cannot say anything, sir. But generally, if you are going to buy a Huawei storage product now, don't buy V3. Right?
Oh, of course. We consider about it. I'm considered about it.
But if you're looking at V5 and V6, yeah, those are newer versions. V3 was out at about 2003, if I'm not mistaken. So generally, it's going to be end of life for it.
Okay, so V6, when is the first launch? V6, 2016?
quite a while back also, actually, about 2013.
2013. Wow.
Yeah, for V5. V6 is generally 2 years old, 2 to 3 years old.
Ah, okay.
So V6 is something. I am suggesting that for the hybrid storage, they're going to come out with new storage products. But from how Huawei works, you can set up a deal with them whereby they will cater for your storage parts or their what they call it, their RMA and all that for the next 7 to 8 years or something.
And about how V6 already equipped with RDMA feature?
Yes. V6 Dorado and V6 All Flash, yes. Anything that uses NVMe, yes.
Oh, okay.
Right. So then we talk about disk enclosures. So disk enclosures are a very simple product. They are basically disk enclosures. What we mean by that? It's basically for your disks, right? So the disk enclosure is you will see the design is exactly the same as the controller also. So if you buy a separation controller and you buy a disk enclosure, the front end will look the same. It will still have the same stuff, right? So if you see the front end, it looks exactly the same. And this is why they have that indicator module and all this stuff, right? So that's why they have the location indicator and stuff, because all the Huawei products look the same, except for the Dorado products, of course. But if you look at the Huawei, yeah, this guy is finally loaded. So let's see here, 3D Experience Center. Let's look at the V5. Okay. So V5, you have the 5500, which is the, let's just say 3.5-inch discs, and the Ocean Store 6500, right? 2U disk enclosure. Okay. Maybe I'll just also do a 4U disk enclosure here. Okay. So the 2U disk enclosure and the 4U disk enclosure, you will see once it loads finished, it looks exactly the same as the controllers. Only the Dorado will look different because the Dorado will have this some fish thing here, right? If you see it, it looks like a fish. They say it's a swordfish. Anybody knows what's a Dorado? So if you go online and you just type in Dorado, you see the image, it's a fish. This is a Dorado, basically. So I don't see anything that looks like a swordfish. Doesn't look like a swordfish, but generally it's a deep sea fish, very powerful, very fast and all this stuff. But yeah, naming sense, yeah, just leave it there then. In terms of naming, very weird naming convention, but yeah, okay. So this is the high density disk enclosure. This 2U and 4U disk enclosures, let them load. It will take some time to load, I guess. But generally, disk enclosures are just disk enclosures. So you only have power module, expansion module, and the disks, right? Other than that, if you compare with a controller enclosure, you will have your controllers. These are the main components of the storage actually, right? With just disk enclosures, they don't do anything. Without controllers, the disk enclosures generally do not work, right? So you have to basically attach the disk enclosures from the expansion module to the controller enclosure itself. Okay, without that, it will never work. Mainly just for disks. However, since you have the hybrid storage series, you have the 2.5-inch disk enclosure and the 3.5-inch. If you're talking about the all flash, you have the 1.8-inch NVMe and the 2.5-inch SAS disk enclosures. Okay, the front end view of the disk enclosure, you'll see, yeah, it's the same. So here they are doing Ocean Store Dorado V6 disk enclosures. So you have the 25-slot SAS disk enclosure or the 36-slot NVMe disk enclosure. You have to remember these numbers, right? So if the question comes out, for SAS disk enclosures, what's the maximum amount of disk for one disk enclosure? 25. For NVMe, 36. right? Then if you look at 3.5-inch disk enclosures, you'll have 12, 3 per row, 1, 2, 3, right? So that's what I'm trying to show you. If it loads, sadly, it's not loading. Yeah, it's still loading. So I wanted to show you the 3.5-inch disk enclosure. So 2.5-inch disk enclosure, you'll see if you do an explosion, it is just the disks, and this is not the controller, right? This is just the expansion module. It's not the controller, okay? So expansion module, if you see properly, look at this guy, change the view. It's basically just to attach your expansion ports, right? So this is a SAS disk enclosure, 3.5-inch disk enclosure. This is 4U, so basically it's 2 units of this guy, right? So this is 2U, this is 4U. So 4U, if you cut half, so basically take this and cut half, you get the 12 disk enclosure, right? But if you have the 4U disk enclosure, basically it's 24 disks in one 4U disk enclosure, right? So this, once again, just disks, right? Then you have your power module and stuff, but it's just disks. Does not do anything else, okay? Once again, disks. This guy, disk plus controller. I mean, this is separation module, integrated module, okay? Any questions? So just using the 3D view, it's much more better, much more easier to see. Other than that, the icons are always the same. So you'll have your disk ID, you'll have a location indicator, your alarm, your power indicator in case of your disk enclosure is connected to a, let's say, controller module, is it powered on or powered off, and the power button itself, okay? Rear view of the disk enclosure, nothing much. You have your serial port, your mini SAS HD expansion for your expansion modules, your ID for your display, so your SCSI ID they call it, your expansion module, the whole thing, your power module, your onboard expansion port, your onboard management port, and of course, for the power module for the NVMe guys. So NVMe disk enclosure be different compared to SAS disk enclosures. That's all. Okay. So whatever they're showing you here is all Dorado disk enclosures, Dorado V6 and all this stuff. So I think the exam is catered more towards Dorado nowadays, less and less towards the hybrid storage. Last time they used to cater more for the hybrid storage, which is the Ocean Store V3 and Ocean Store V5. Nowadays cater more for Ocean Store Dorado. That's it for these enclosures. So you guys okay to continue, or do you guys want to take a short break?
Maybe better get a short break.
No worries, sir. No worries. I know it's a lot of theories. So no worries, no worries. We'll take a short break. Okay, let all these guys load up. Right. So current time for you guys will be 2:50, right? So we'll be back at, let's say, 2:30. So 15 minutes left. Is that all right with you guys?
Okay.
Okay.
All right.
Okay, sir. Yeah.
No worries, no worries. Rest yourselves up, and we will be back shortly. All right, guys, we are back. Okay, so we'll continue on from where we left off. So now we are going to go into expansion modules. So hope everybody is fresh, everybody's okay. So expansion modules, if you're talking about the Ocean Star Dorado, you only have two main expansion modules, which are the 2U SAS disk enclosure expansion modules and the 2U Smart NVMe disk enclosure expansion modules. So if you're using NVMe, then you'll use this expansion module. So this guy. If you're using SAS, then you will use this guy. Right? For switches, of course, here is using what they call the CE switch. This is generally quite a powerful switch. It's not cheap in the market because they have basically 48 times 10 gigabyte Ethernet electrical ports. These are generally, so I think it will cost you about at least 10 to 15,000, or maybe, yeah, it's about 10,000 or maybe about 8,000 USD. So it'll be about, is it 5,000 USD? Something around that. So it's pretty expensive in some sense, right? So depending on what kind of connection you're using on your storage backend, you will use the appropriate switch, of course, right? You cannot have a 100 gigabyte Ethernet storage connection and the switch only supports 10 gigabyte Ethernet. You're wasting the module itself. Although they can still run, but you're wasting the module, right? If you're running SAN environment, fiber channel switches are there. Huawei has their own brand of fiber channel switches. It's actually a redistributed switch from a company called Brocade, right? Right. So Brocade generally creates those switches. So Brocade is like the sole provider or the main provider for fiber channel. Huawei buys Brocade switches and rebrands them as Huawei switches. So here is an example of Huawei SNS 2124. If you're familiar with fiber channel and Brocade configuration, the SNS series will be the same. So Huawei does not create their own fiber channel switches. Huawei tends to move away from fiber channel because fiber channel itself is slowly but surely losing track, right? So less and less people are going towards fiber channel because of the price. Fiber channel switches compared to normal Ethernet switches are at least 2 or 3 times the price. Okay. So if you're using fiber channel, you buy the fiber channel switches. Here is an example of, I think, 16 gigabyte Ethernet fiber channel. That is the Huawei SNS 2124. Device cable, so of course, depending on what kind of backend environment you're running or front-end environment you're running, if you're running like serial connections, mini SAS HD, optical HD cables, AOC cables, quad SFP, SFP28, 14 data rate cables, MPO cables, optical fiber, depending on what kind of fiber cables you need, you will find them, right? It is advisable that you choose your SFPs or your small form pluggables and your cables together, right? Right. Then we go into disks. So disk types. Huawei supports all these disk types, right? Huawei does not support 5.25. But there is a 5.25 inch disk outside there in the market, so it's there. But Huawei supports 1.8, 2.5, and 3.5. However, for 1.8 and 2.5, this is support for all flash modules. So SSDs, right? If you're using the hybrid controller, then it supports these two guys. Right? So most generally, if you're buying hybrid controller, that means you're buying the base product lower end here and there. But they support 2.5 inch and 3.5 inch discs. Okay. All flash controllers only support SSD. Hybrid controllers support both HDD and SSDs. Okay. Interface type that Huawei supports, you have of course IDE, SCSI, SATA, SAS, FC, NVMe. Huawei supports SAS and NVMe, right? Fiber channel connectors, SATA connectors, SCSI, IDE. Basically, SATA in a way is supported because they use SAS connectors, but yeah, generally you will not see SATA connectors that much anymore. But you can still backward compatible, so no problem. But Huawei only supports SAS and NVMe connections, right? But these are all the different types of disks. Application scenarios, of course, depending on your situation, maybe you're doing enterprise class applications, desktop class applications, no problem. That is on your own environment itself. The storage controller can support any of those environments, so no issues there. But for, of course, enterprise class environment, if you're a huge enterprise, you will look to merge more on performance. So generally, huge enterprises will tend to favor more SSDs for their applications and HDDs for their archiving. And they generally use 3.5-inch disks for their archive and 2.5-inch or 1.8-inch for their running environments, right? So all best practice. There's all situations, right? So whatever situation you're in, that's where you have to start building your storage backend. So if your company is more towards running more applications online, less on archiving, you might want to look on more high-powered disks, SSDs, flash disks. If you're running more archiving purposes, backend, you need a lot of storage. Maybe you just want to save something in HDDs, much more cheaper if you just use those SAS disks, 3.5-inch SAS disks. No issues there. So it's all situational. Okay. Now we look at the structure. A lot of questions can come out from here, so I'll go through them one by one. So this is a structure of a hard disk drive. So a hard disk drive, you will have an actuator arm, a disk platter, spindle, of course the port. So the port, you can just say this is the connector basically. Okay, that's the port, and the read-write head. So how it works, okay? So the platter and the spindle actually work together. The spindle spins the platter. So this is the guy that's spinning the disk, right? The platter is just basically where you save data. In the platter, you'll have multiple disks. Later on, we'll see. How you read and write data is actually using the actuator arm and the read-write head. So the actuator arm is this guy. Okay, you can say this guy is the actuator arm, and this will be the read-write head. Okay, so this small component here, they'll have a small, it'll look something like one small dot coming out here. That small dot there will be the read-write head. So you can go and open up a disk, you can check it out. Okay, so you can see here, there's a lot of mechanical parts. And the problem with this kind of products is actually mechanical parts. So let's say you buy the disk today, and then something goes wrong with the disk platter. Because it's mechanical, anytime it can go wrong. Maybe the disk platter is not spinning properly, not enough RPM and all that stuff. You don't get your data on time. So then, hence, your read and write operations are a bit slower. And to find data, the read-write head must actually basically go on the disk to find the sector, to find the platter and all these things. So it takes a long time. Even though the disk spins very fast, we see it spinning very fast, but in terms of storage, this is actually very slow. Okay. So everything here is a mechanical component. Read-write head, actuator arm, platter, spindle, even the port itself is a mechanical component, but the port, yeah, generally doesn't go down at all, unless there's some issues with the actual, like say all these physical, physical components. But the ones that can fail here are so many things. Okay. So working principles of HDD, you have your platter and you have, of course, your spindle. The read-write head or the actuator moves the read-write head on the magnetic disk to find the data. Okay. So the distance between the head and the disk is small. So you can see a very small distance. the platter is driven by a motor. So you'll see a motor later on. I think that's the next one. Yeah. Okay. So that's how it works. So basically, the platter will spin using the spindle. The spindle will spin the platter, and the read-write head will then go to the sector or go to the platter itself and find the data. And this is how it generally looks like. Okay. So under the spindle is a motor that moves the spindle. And in the platter itself, you have multiple cylinders. So if you actually look at a disk, so if you take a disk, let's say a HDD, okay, or HDD, yeah, here's a good example. Man, cannot go on this picture. Okay, here, okay. So you can see here. Okay, so you can see here, there's actually multiple platters. These platters are called cylinders, right? So this whole thing is called a platter. You have multiple cylinders in a platter. Each of these cylinders is basically a disk or space where you read and write data. You can compare this to like a CD-ROM and stuff, right? Similar concept, okay? So you have multiple like CD-ROMs here. All those CD-ROMs are where you save your data. But in storage HDD, these are called sectors. Or cylinders, sorry. Okay. So each cylinder will have a set size of how much data you can read and write, right? So the more disks here, the more cylinders you see, basically the more disk space you have. Some come with terribly a large amount of disk space and all that stuff, like this guy. You can see here, multiple cylinders here, right? Each of them have their own read-write head, right? So all these are read-write heads. For each cylinder, there is a read-write head here, okay? Anytime this guy can have issues at any time, okay? So that's how this platter actually works, okay? So for each cylinder, you'll have multiple actuator arms and the read-write head. So how the read-write head works to find the data, inside a cylinder, you will have sectors. So you have multiple, so like you take a disk, you'll have multiple sectors. So sector 1, sector 2, sector 3, and all this stuff. These are all sectors, right? Oh, sorry, these are all tracks, my bad. So these are all tracks. Inside those tracks, you'll have multiple sectors. So let's just say something like this. So this will be sector 1, this will be sector 2, 3, and so forth for this track. Then the outside track will have more sectors. So it just keeps going out this way. And that's how you actually use the read-write arm. So the read-write arm will have to go into the sector, go into the track, find the sector, and then you can find your data. This is all done mechanically, right? So there can be a lot of issues whereby you have delay on the read-write arm, delay on the spindle, delay on the motor, okay? So many things. But generally, this is how this works, okay? So what you have to remember is this guy. Disk capacity. So disk capacity is the number of cylinders times the number of heads times the number of sectors times the bytes. 512 bytes by general. That's how many MB or GB units of storage space you have. Okay. So you have to find the number of cylinders you have in a disk, the number of read-write heads. So you'll probably like say you have 7 cylinders, 7 read-write heads. So 7 times 7, you get your 49 there. The number of sectors, so that will be at the back of your disk. So you times the number of sectors, then type 512, and you see how much disk space you have. The cache. Cache component is basically random access or volatile memory component. So because of the processing speed of CPU, is much faster than of a disk. The CPU must wait until the disk completes the read-write operation before issuing new command. To solve this, that's why we have the cache. So remember, when you have a storage controller, your data is actually written into the cache in the storage controller first. So once it's written into the storage controller cache, then it's flushed out into the disk, right? because of this slow component, right? So that's why they write it into the cache first. So once it writes into the volatile or flash memory, the cache itself, then it slowly flushes out into the actual storage space, which is the disk itself. This process will be an ongoing process because they'll slowly flush out the cache over time. There's a large amount of data coming in. They'll fill the cache, then flush out the data at the back end, and then fill the cache again, flush out the data in the back end. This is how storage controllers work. This is why you see the speed suddenly is fast, even though you're using like HDDs. It will be generally faster than just directly trying to save it into the disk, okay? Because of the cache technology. So factors relevant to disk performance, this you need to know. Rotational speed, seek speed, single platter capacity, and port speed. So rotational speed is basically talking about how fast the disk can rotate. Okay, so the disk platter can rotate. Seek speed is how fast can the read and write arm seek the data it wants. Okay, single platter capacity basically telling you a single platter, how big is the capacity itself. So that in some sense also leads about how much space you have and all that stuff. It's another indicator for disk performance. In some sense, the less capacity, the faster the seek speed, right? But less capacity meaning is not really that useful anymore, because hard disks nowadays are mainly used for capacity purposes to save a lot of data. They don't really care about speed. We just care about saving as much data as we can. That's where we use hard disks. If you want to talk about speed and all that, we generally tend to not look at hard disks. We tend to look at SSDs, right? And finally, port disk or port speed. How fast can the port connect to the storage controller and all this stuff? Okay. Average access time. So average access time is determined by average seek time and average latency time. So seek time basically is how fast the read-write arm takes to seek the tracks and the sectors and stuff. That is called seek time. So by default, the read-write arm will be always placed somewhere here. So this is called seek time, right? How long it takes for this head to move here. Then you're talking about average latency time is how long. So now it's moved to this track, right? So now it's correct. It's waiting on the correct track. But how long maybe the data is here, right? So how long data from here to go to here? That is basically average latency time, okay? So seek time is moving the head, the read-write head. Latency time is like I'm looking for this block of data. How long it takes for this block of data to move into my read-write head. The data can even be here, right? So the disk will only rotate in one manner. So the disk will always rotate this way. Your data can be located here. So some data here, down here, sorry. So how long does it take from here, this guy to move from here all the way to here? That is your latency time. This can be an issue, or it can be basically how you calculate your average access time. So if the seek time is slow, so if a read-write head takes a long time to move here, you have an issue, right? Basically, it takes a long time to just go and look which track is it. There's some kind of something wrong, maybe with the mechanical part or something. Then maybe the spindle might have some problems. So it's not moving the disk as fast enough. Supposed to be like 10,000 rotations per minute or something like that. But yeah, can be issues, okay? Data transfer rate. So data transfer rate is determined by internal transfer rate and external transfer rate. Internal transfer rate is basically, yeah, you have your seek time, you have all this. How long does it take internally to transfer the data into the chip, and how long from the chip to transfer to your like say your server or something like that, right? So this will be the external part, your server here. The internal part, everything that happens in the disk. Okay, it's easy to understand concepts, kind of, right? Then you have Iops and transmission. So Iops is something called input-output operations per second. This is one of the key indicators, like they say, to measure a disk performance. Iops is calculated by seek time rotational latency, and data transmission time. All these three things together. Once IOPS is calculated, then you'll know how many input, output, or how many reads and writes and all these things you can do per second, right? Transmission bandwidth, or what we call throughput, indicates the amount of data that is successfully transmitted in a unit. That is the speed at which the data is streamed at, right? So you can take the example here, you can look it through, but these are some indicators, okay? IOPS and transmission. So generally, if you go at the back of a disk and you see the IOPS is very high, that means the input, the data transmission rate is fast. It's very, very fast to save and read and write data here, right? Parallel and serial transmission. So in some sense, parallel transmission is actually faster than serial. Okay, but yeah, with nowadays technology and all that, that's different. But if you check back in the old days, parallel transmission basically transmits data 1, 2, 3, 4 in a parallel line, right? But the problem here is maybe the what do you call this transmitter here is faulty. So this data all goes first. These guys all reach the end, and then this data doesn't reach the end. So that's where situations and data error situations can happen. So parallel transmission, yeah, it is fast, but compared to serial is much more, let's say, safer in some sense. So they transmit data in packets of 1, 2, 3, 4 in a line, right? So only one line is connected between two ends. 8 numbers are sent in this line sequence. To receive the end, all 8 transmissions have to be sent. Once that is received, then yeah. Okay. For parallel, multiple lines are connected between two ends, and one number is transmitted on each line. So they'll never know if this data has reached and this data has never reached. They'll just take it as information. They'll just take it as data in that sense. But with serial, you have a start and end bit most likely. So you always have like start bit, end bit. So they'll know, okay, full transmission has been done. Start bit, end bit, right? But if you're looking at speed, in some sense, parallel technology is still faster. If everything goes well, parallel technology is still faster than serial in some sense. But serial technology is much more, let's say, reliable, right? But nowadays, yeah, serial technology has way overtaken parallel technology. We always either use serial technology or newer age technologies. So any questions first before we go? I'm just going through the slides here and there, but if you guys have any questions, do ask me. Ooh. Right, disk port technology. So a disk must provide simple port for users to access data. There are different types of disk port. You have ATA and SCSI instruction systems. So ATA, you have IDE ports, which are the old connections. If you remember the old PCs and all that, they used to use IDE. You also see SATA connections. You still see SATA ports, some like older storage nowadays. But generally, yeah, we tend to try not to use SATA as much. Okay. But of course, if you're going with a cheap disk and all that stuff, maybe you still have SATA ports, no issues. SATA disks in that sense. Then you have parallel SCSI, and you have serial attached SCSI or SAS, and fiber channel, of course. Serial attached SCSI is currently the main technology used for low-end storage systems. You see less and less of SATA technologies basically going to be phased out sometime soon, I guess. Some users are still using it, but they are planning to phase it out. Generally, we start straight away with SATA, SAS ports, and then we move to like NVMe or fiber channel and stuff. For fiber channel ports, there was a disk like fiber channel ports last time, so you can see on the internet. So a lot of these things I will show you basically from the internet. Let's say fiber. Yeah, so this will be how a fiber channel disk is done. So you'll have a fiber channel connection. It's a bit different from what you generally normally see. So normally you'll see like SAS hard disks or SAS connectors, something like this, right? Some kind of serial connection like that. Fiber channel, yeah. If you see a fiber channel port, there's the guy, fiber channel. Yeah, generally looks a bit different. At the time when fiber channel created, it was a very good connection. I would not say it's bad, right? But it was generally very expensive. So even if you see now, right, it costs about 295 USD for a, yeah, I don't think it's a very big disk space also. How big is this guy? You know, but yeah, 295 USD for disk. You can generally buy a SAS port for much more cheaper than a fiber channel disk, right? For the same size. So fiber channel generally was phased out, not being used anymore because it was just expensive. So the ones used nowadays, this guy is not used, this guy is not used, this guy is not used. This guy also tend to be not used. We tend to use this guy. Huawei supports by default SAS and NVMe connections only, okay, on disks. So IDE port is the old days, integrated drive electronics, that's what IDE means. ATA stands for Advanced Technology Attachment. Yeah, just remember we don't use ATA or IDE, ATA and IDE ports anymore, right? SATA port. SATA is short for serial ATA. Okay, you have 3 versions of SATA. Basically, the transfer rate is from 1.5, 3, and 6. You will see SAS doubles this number. So SAS will start at 3, then you go at 6, and then you go at 12. Current environment supports up to 12 gigabyte SATA SAS disk. Okay. So basically, SAS is an upgraded version of SATA. Okay. So SATA uses serial transmission, provides definitely higher transmission than IDE. SATA also uses point-to-point architecture and supports hot swap over. You need to know this for the exam. Okay. SCSI ports are generally not even seen anymore. Maybe on old printers or something you can still see, but yeah, for disk connections, no. Because there were too many different types of SCSI connectors. If you go and check out SCSI connectors, SCSI connector. Okay, go to images. Yeah. So there were too many different types, maybe this guy, so many different types of SCSI connectors. You have the male pin 25. You have the low density 50 pin male. You have the low density 50 pin female. So yeah, so many different types of port. And then if you want to get the correct connection here and there, you have to find the correct, like say the attachment and all these things. Generally had so many issues there, just because of the port types. So they standardized it, and that's why we have like SATA, and then we have like IDE, and of course SAS itself. So that was the main problem for SCSI ports. SCSI as a protocol is still used, but as a physical port, it's not used. SCSI protocol you'll still find in virtual environment. So virtual machines will still use SCSI connections. Physical environments, they don't use SCSI connections anymore. Okay. SAS port. So SAS is short for serial attached SCSI. SAS is a point-to-point full duplex port. SAS is backwards compatible with SATA. Rate is about 600 MB per channel. SAS features high performance, high reliability, and powerful scalability. Okay. Then we have our good friend fiber channel. Fiber channel, yeah, you see them as server to storage connections. You don't see them on disks anymore. Okay, so you won't see this guy anymore. You will still see this this guy, right? So like fiber channel cards and all this stuff, you'll still see, but on disks, no. On disks, you won't have a chance, right? Maybe for other storage products other than Huawei, maybe you still see them, but for Huawei, no. Okay. So fiber channel uses fiber channel arbitrated loop or fiber channel AL. Supports dual port serial storage interface based on SCSI, supports full duplex, universal hardware transmission, and all this stuff. So universal hardware transmission doesn't matter what kind of hardware you use, as long as you use a SCSI, a fiber channel connection, they are able to transmit the data. So most likely you have to have a fiber channel HPA, and then you can transmit the data here. That no issues there. So that's for hard disk drive. So main thing you need to know is how less reliable hard disks are, how it can have issues with average seek time, average latency time, and then the types of connections here and there. SSDs we'll go through now. So SSDs basically are flash disks, right? They use NAND flash to save data, generally much more powerful than hard disk drives. At least the base SSD will be at least 2 or 3 times more powerful, more than 3, maybe 4 times, right? More powerful than HDDs. Comparing the Iops on SSDs and HDDs, you'll see a lot of difference. Like in Huawei cloud environment, you can still buy HDDs for their cloud disks. You'll see Iops like 2,000, 5,000 Iops maximum. SSDs can go to about 33,000, 50,000 Iops, no issues. The good thing is it has no mechanical structure, so it has no mechanical parts by itself, and it consumes less power than hard disk drives. Because hard disk drives, you require power to move their mechanical parts. Solid state disk does not have mechanical parts, so it consumes generally less power and less heat is created from the disk itself, not including also the noise. Hard disk drives, if you have like a PCs at home and all that, and if you're like a gamer or a 3D designer and all that, at some point, like you're generally running a new software, you can hear the hard disk spinning, right? Very, very noisy, very, very irritating sometimes, right? Solid state disks, you won't feel that, right? However, the life cycle of solid state disk is determined by the number of what they call PNE or PNE cycles, which is a program and erase cycle. Because every solid state disk will have its what you call cells. It'll have multiple cells. Every time you're writing data into a cell. When you're erasing data out of a cell. Because it's a flash memory, each cell has basically what they call a determined life cycle, right? So how many write and erase you can do per cell. So each cell, maybe you can do 70,000 writes and erase, which is pretty awesome. 70,000 writes and erase per cell. So you can write the data. Once you don't need the data, you can erase the data, write again, erase, write again, erase 70,000 times. Once 70,000 times is done, that cell is no longer usable. So each cell will have its own lifespan, right? This is how it's calculated in program and erase. So in that sense, at the back of an SSD, you might see the life cycle of an SSD shorter than of those in HDDs, because HDDs can go up to 600 years and all these things, but mechanical parts. So because of the unreliable mechanical parts, HDDs are basically not used to save your everyday data. The everyday data, like you're going into work, you're doing work online, offline, and all these things, generally try to use SSDs for that. Databases, SSDs. Archiving, then you go put it into your HDDs or your tapes and all this stuff, right? SSD architecture. So SSD controls of a control unit, or what we call the main flash memory chips. So the control unit is the SSD controller, host interface, and the DRAM. Storage unit is the NAND flash RAM, right? So generally, SSDs, inside the SSD, they have their own cache, kind of, right? So the RAM here acts as the cache. So when the host connects and sends data, they go through the processor, data is saved into the cache. Same how it works in a storage device. So all your frequent data, your new read and writes goes into the cache, and the cache then slowly flushes it out into the NAND flash, right? It generally works the same. So inside SSDs itself, the cache is there, which is very powerful. So when you're writing data into an SSD, you're writing data into the RAM of an SSD in some sense. Once the RAM is, like say, close to full, it'll flush it out to their backend flash cells, which is the NAND flash cells. And this is how it works, right? Any questions? Cool. I think everybody already falling asleep. No problem, no problem. Told you it's going to be boring first day.
Can you go back to the previous slide?
Okay, no worries. Yep.
So there is a processor inside, right?
Yes.
No. The previous slide, before this. Okay. The program and erase cycle. Usually, how many times the cell will be broke, getting problem? Program and erase, how many times usually?
Oh, that is depending on the vendor, man. So like high silicon and all that, different vendors have different program and erase cycle. So that depends on the vendor itself, the vendor product.
Okay, let's say in the HDD, usually we know that about the bad sector. Is it similar to the SSD?
Bad sectors? Yeah. So bad sectors are basically like data that you delete halfway or something like that, something went wrong, right? Bad sectors. So it can still happen, like you are writing frequent database inputs and outputs. If you write the data too fast here and there, you can have a bad sector. So yeah, generally, yeah.
You know, it means in HDD when we facing a bad sector, it means the application or the program may give a sign or indicate that this sector cannot be written or cannot be write or read.
Yeah.
Meanwhile, in SSD, is it possible for some application give a sign to some cell to an SSD?
So generally, how the storage controller works is, so the intelligent storage controller will have an O&M sequence inside the storage controller, right? That O&M sequence will connect to the disk. So basically, the O&M sequence will connect to the disk and it will keep scanning the disk. So you will also scan on the cell levels. So like say this cell level has 300 PNE cycles left, right? So this is one application, right? So 300 PNE cycles left. So it will generally send you an alarm, will notify you using the bell icon and all that stuff. It will send you an alarm via email or something like that, and tell you there is this SSD has left like 300 PE cycles for this sector and all this stuff. So you might want to change this SSD. Okay.
So every vendor has a different number of PE cycle.
So they might start off with like say 70,000, right? So they start off with 70,000 PE cycles. Every time you write the data, now you're left with 59,999.
Okay.
So it will just keep reducing until the cell itself doesn't work anymore.
Is it possible for us to know the condition of our SSD status right now about the
That
PE?
usually is done by the storage controller management. So the storage controller will tell you, okay, this
is there any application how do we read? Can we read the PE cycle right now on the existing disk?
SSDs. There are certain applications, but generally the storage controller management itself will do it. So if you like using NetApp and all that stuff, NetApp storage controller will already tell you because they know the right cycles and stuff.
Okay. I mean, if we use like laptops or desktop PC, is it possible for us to know?
Yes. Definitely there is a software. Forgot the software name though. If I get the software name, I'll give it to you. I had a friend who was using it, so I'll just contact him and see what he's still using.
Okay.
No worries, can be done. But you will need connection to the storage itself. Then you have to scan the disk and all that stuff.
Okay.
Possible. Okay. Any more questions? Cool. So this is how the NAND flash works. So you have the internal storage unit or the NAND flash, which includes LANs, planes, blocks, pages, and cells. Cells are the smallest unit. After cells, you have pages, then you have blocks, then you have planes, and then you provide the LAN. LAN is basically the actual storage space provided, or what we call logical unit number that we provide to the service. So operations of NAND flash include erase, program, and read. These are the only 3 operations. So erase and program, basically, you want to write or you want to remove. That's it, right? NAND flash is non-volatile medium, so a block must be erased before new data is written. That's why you have the life cycle. So a program and erase cycle is a process of erasing a block and then writing it again. So you keep writing and erasing the same block. Of course, that cell or that plane and all this stuff will have less read and write cycles or P&E cycles, right? Then we already went through this. Sorry, haven't eaten something since morning, but yeah. So if we go through this, so you have the cell levels, right? So this basically explains the different types of cell levels: single level cell, multi-level cell, triple level cell, and quad level cells. So you can see here, SLC supports up to about 50,000 to 100,000 P&E cycles. MLC supports about 3,000 P&E cycles. TLC supports about to 1,000 P&E cycles. Why? Why the more higher the size, the more less the write and erase cycles? I can tell you why. So let's say your data is like 101, right? If you're writing it in single level cell, they will just write 101, probably another cell down here. Okay, but if you're writing it into MLC, you'll write 10 here and 1 will come down here, right? So generally, if you're trying to erase this data, you will erase both these cells, even though this cell has another data you can save. But generally, it will just erase these cells, right? So that's why you have less program and erase cycles because of how data is configured. So for this guy, if the data is just 111, then it's all right because he will just enter the first cell. But if the data is 1110, you're basically going to erase this cell and erase 10 here. So to erase this 0, he has to write back this, maybe it was 011. So you have to erase the whole thing, write back the new data, and then put the 11 at the back. So generally it takes more work, and hence you get more capacity, but you get less P&E cycles or program and erase cycles. And then you have quad level cells, which basically does more and all this stuff. However, if you talk about capacity, of course, this guy will be the highest amount of capacity you get compared to the other, everything else here in the menu, right? But that's why you see this guy, much more program and erase cycles compared to all the other guys. You'll see a big drop in program and erase cycle when you use MLC to TLC to quad level cells. Quad level cells, they don't even tell you how many P&E cycles left because they don't want to show you. You must, however, understand this is for each cell, right? So we're talking about cell. Each cell can contain to a plane or a block. So it will look something like this, right? So you have a cell. A cell is basically a part of a page. A page is basically 146,688 cells in one page. One page is basically in a block of 768 pages become a block. Then after 768 pages become a block, a plane consists of 1,478 blocks, and then a die consists of 2 planes. So you can see here for each cell 3,000. So this guy 3,000, this guy 3,000, this guy 3,000, this guy 3,000. Okay. So if you put them all together, yeah, you have a lot of read and write cycles, right? Even if you say like, if you look here, it looks like, okay, after 3,000, that means the cell is gone. But you must understand the technology whereby cell, plane, block, pages, and die, right? So you have actually a lot of space, a lot of time to do your write and erase. So it will not basically spoil in just one year, unless you're doing super intensive read and writes. So you write and then you erase. Every 1 hour you write and erase of about 50 GBs, 100 GB, 1 terabyte per hour. You write, then you erase, you write, you erase. Yeah, then maybe your cell will die faster. But generally it doesn't, I don't think there's any application that does that currently. Maybe big data or whatever, but yeah, I don't know. So you have to understand this concept. Cell, page, block, plane, and die, right? So a cell is what we were looking at. Each cell, yeah, can contain, like for SLC, each cell can contain 1 data. For MLC, each cell can contain 2 data. This is what we were looking at. But if you look at the big picture, yeah, you don't have to worry that much that it's going to fail in the next 2 hours or 3 hours or something. It can last generally about 5 years plus on a normal routine. 3 years maybe on a intensive read and write architecture and stuff, depending once again on your cell level, right? So you need to understand cell, page, block, plane, and die. Why? They can actually ask, I have seen this question come out. What is the relationship of or the flash chip relationship, right? They'll just come out with a question like this, and then they will come out with A, B, C, D. A, page to block to cell to plane to die, right? So you need to know exactly how it works. So you have to start with cell to page to block to plane to die. That's all, right? Just remember that. Should be good for the exam. Okay. After exam, yeah, can't forget about it. Don't worry about it. But during the exam, you just need to know, yeah, these things. So just for the exam, kind of have to just remember certain stuff. There's a lot of things I understand, but it's the way exams go, man. Address mapping, they use like a logical block address and physical block address. So for HDD, the relationship between logical block and physical block is fixed. The relationship for SSD is not fixed, what they call the non-override. So a block must be erased before new data is written to the new data and the old data are at different locations, right? For HDD, the relationship between LBA and this, so it basically overwrites the data. So if you want to replace the data, it just overwrites the current location of the data. For SSD, it will really basically, like, just put it this way. Let's say you in a SSD, okay, you have 4 blocks. Your actual data that you put in is 1, 0, maybe somewhere here, these 2 cells. Then you have new data coming in, 0, 1. It's just an update of the current data, so it's the same file, but you did an edit and all these things, right? But you want to update this data into the SSD. What they will do is actually, they'll erase the 1 and the 0, and they'll probably put the data 0, 1 here. So they'll erase the previous data. That's how the P&E cycle works. However, for HDD, okay, so let's just put it in a block scenario. So you have data 1, 0. If you have data 0, 1 coming in, this is the same file, let's say, but you edit it. It comes in. It basically replaces this guy. So this guy will just come 0. This guy will become 1. Right? It replaces, it overwrites the data. It does not write or erase. It just overwrites the data. SSDs, they don't overwrite. They erase first the previous data, and then they write the new data in. That's how it works. Make sense? No problem? So usually there's a lot of questions here. Okay. Now if you understand this relationship regarding...
maybe I have asked a question.
Yeah, go ahead, sir.
Okay. How to identify the addressing at that location? in SSD.
So how the SSD does
Addressing.
addressing, that is this is how they do addressing. But yeah, it's going to be pretty hard to imagine, because they will write the data into cells, then the cells will go into that planes and blocks and all these things. So if you look at SSD, how they write data, this is how they write. So if you're writing 4 KB of data, you'll just write it into your block, right? 4 KB block size there. If you're writing 16 KB of data, basically each block is 4 KB. So you need to know your block size, right? Make sense?
Okay.
Right. So are you confirmed, sir? If you don't understand, then yeah. But then every time it's like, okay, like writing a block of data. So let's just take the same block again. So every time when it writes data, so like say you write a file called object.txt, right? Sorry. J-E-C-T. Object.txt or something. The object.txt is basically, if you change it to computer language, is 10. Let's just say, okay? Inside the object.txt, it's a text file. You have 1 and 0 here. Let's just say, right? So this is the object.txt. You save the file. It basically saves it into the SSD as 1 and 0, right? In whichever block here and that. Okay. And then you make an edit to this file. So you change the 1 and 0. Now you put 1, 2 or something in the file. They will basically change the object. So now the actual file is called, if you change it in computer language, is 1, 1. However, to write the same file, even though it's called still object.txt, to write this here, they will first erase the previous file and write 1, 1 again. So it might not write it in the same place, it might write it in the same place, depending. Most likely it will never write it in the same place, but yeah. So that is the address mapping sequence of SSD. SSD is the hard one. For HDD is simple. HDD, same thing, you have a block, okay? You're writing same object file, so your file initially was object.txt, you got 1 and 0 inside the file, you upload it, right? So the file be 1 and 0, okay? You make changes to the file, now it's 1 and 2. They will just erase or just override this 0 here to become 2 in the same location. Does that make sense, sir? Or is that what you're asking for? Or it was something else?
Okay.
I know, sir. If it's a different question, do advise. Right?
Right.
Okay. So if it's okay, then we'll continue. If you still have some not clear about something, do tell us, sir. No issues. No issues. Cool. So FTL. So this is how it works on basically what you're calling it hard disk drives. So when you're writing data into a hard disk drive, you're writing data into sectors. Sectors are into tracks. So OS sector might be 512 bytes. So each sector might be 512 bytes. So file system writes a unit of 512 bytes. So if you have multiple 512s, multiple sectors will be used up. FTL mapping operations. So the main controller maps the address based on the mapping table. So like where to find the data. Okay. That's it. Okay. So if you're using NAND storage, then yeah, NAND, this is in terms of like SSDs. SSDs, they use cell levels and all that stuff. But in your storage itself, you will basically say your application, so like your server will know where to find sector 1, where to find sector 0, 1, 2, and all this stuff. You'll have a mapping table in that sense. That mapping table is saved into your random access memory or something, right? And, but yeah, that's how it works for hard disk drives. So basically the server keeps in track of which sector and all these things. Solid state disk, when you're writing data, you're writing it into blocks. Okay, so each block will contain a size. So depending on how many blocks you use, if you're writing like 4 KB of data, yeah, you just write it in one block. Writing 16 KB of data, multiple blocks, multiple SSDs and multiple channels and all these things. Okay, until all the blocks are full, then your SSD cannot write anymore. You have to probably delete something and write off some stuff. Okay. Data process written on SSD 2. So when SSD is full, all data must be deleted, okay, to release new space for new data. So that's what they're telling. So when a user deletes and writes data, in some blocks becomes invalid or aged, and they have certain like bad sector issues and stuff. Data reading process. So if you want to read data, they'll just read the 4 KB of data. You can read 32 terabytes or 32 kilobytes. Yeah. Okay. So basically, it's according to the blocks. The read and write process, actually, I don't know why they put it here, but nothing much to talk about. Sorry. So nothing much to talk about. But yeah. Any questions? Cool. Then you talk about SSD performance. Any, no questions, sir? No problem. So somebody maybe had a question to ask? No? All right. So SSD performance advantages. You compare SSD and hard disk drive, definitely you have a lot of differences there. So first of all, you have the mechanical seek time problem on HDDs. SSDs don't have any mechanical products, right? Nothing mechanical inside a SSD itself. So generally you already have way better performance compared towards hard disk drives, right? Power consumption. So power consumption here is just an example. So 2 SSDs are basically equal to 250 HDDs in terms of, 250 HDDs take a lot of power. By to compare like the performance and all this stuff, 2 SSDs performance is like 250 HDD performance, but yeah, power consumption will be generally very high. Okay, this is just putting it in plain picture, the performance, right? So for as much performance as you get on 2 SSDs, you get on 250 HDDs. I don't know whether that will be a very, very general concept, but if you regard the number of Iops, yeah, maybe. Use of SSDs in storage system, random read and writes. So class A applications, high concurrency applications feature random read and writes, databases. Large files and image streaming media features such as sequential read and writes, data backup or rarely used applications. I would suggest SSDs you use for class A, right? Always use SSDs for class A. Class B and class C, that depends on what kind of disk you want to use. Class B, maybe SAS. Oh yeah, so they already have the graph down here. So yeah, SSD you will always use for databases. Like your large images and all that, yeah, you'll use SAS disks. And for your backup and archiving, yeah, we'll use SATA and LSAS disks, right? And LSAS is basically SATA disk with SAS connector, right? There's a bit of difference there. It's called nearline SAS. We'll look at the disk later on. Okay. Right. Then I think after this topic, we can take another short break. I know the first day is always boring, man. I can understand if you guys are sleepy and all this stuff. Yeah. Raid, day 2, I think we'll look more into raids and all that stuff. So that will be a bit more on, let's say, a bit more technical. So I know you guys maybe have much more of a technical, what is this, audience? Nobody here from project management, right? Like teaching project management or maybe like all infrastructure guys, correct?
Yeah, I think.
Just double checking.
Not
cool.
yet.
So just double checking if you guys are all infrastructure guys. Else, yeah, it will be, when we start going to technical stuff, it'll start getting complicated. Because if your guys are all from network background, then we can start using some network terminologies, make it easier for you to understand. Right, so we'll finish the interface module, then we'll take a short break, don't worry. So interface modules, of course, we're talking about the front-end interface modules and the back-end interface modules connected to the storage controller. So Huawei has Gigabyte Ethernet interface modules. So you have the, what you call the electrical 1 gigabyte Ethernet interface module. You have the 40 gigabyte Ethernet interface module, and you also have the 100 gigabyte Ethernet interface module. Generally, you don't see these guys being used that much. These guys are still seeing being used, but for high-end environments, these guys, you'll see them everywhere. The other one will be the 10 gigabyte Ethernet, but yeah. Expansion modules, so if you want to talk about expanding your storage controllers to your disk arrays, you have the SAS expansion module or the RDMA interface module itself. SAS expansion module, you have the 12 gigabyte SAS expansion module. This is the basic one, which you will see everywhere. For RDMA interface modules, you have the 100 gigabyte RDMA module or the 25 gigabyte RDMA module. So if you have a plan to use RDMA, this is for Ocean Store Dorado or Ocean Store All Flash, then you can use these guys, right? Generally, the hybrid storage product, you will generally see this guy. Hybrid storage product, you will generally not see RDMA, right? But for Dorado and All Flash, yes, you will see the RDMA product. Smart I/O module. So a lot of questions usually come out for this guy. So what is a smart I/O module? Generally says, depending on what type of SFP, so depending if you like have a fiber channel SFP, you plug in the SFP into the module, it will run fiber channel. If you have the Ethernet SFP, so if you're running Ethernet SFP, you plug in the Ethernet SFP into the module and you'll run Ethernet. So Smart I/O caters for both fiber channel and what do you call this? Ethernet. Now they have split it into two for some reason. Last time they used to have one Smart I/O module, but now you have the fiber channel Smart I/O module or the Ethernet Smart I/O module. So the Ethernet Smart I/O module I think goes up to only 25 gigabytes. So even if you have like a 10 gigabyte module, you plug it in here, it will run 10 gigabytes. So 1 gigabyte module, you plug it in here, it will run 1 gigabyte. Fiber channel, same thing. If you have 32 gigabyte Ethernet fiber channel module, 32 gigabyte fiber channel module, sorry, not Ethernet, you plug it in, it'll run 32 gigabytes. But if you have a 15 or 16 gigabyte fiber channel module, you plug it in, it will run 16 gigabytes, right? So basically you can use plug and play whichever module you want. The previous guys, like these guys are all stringent. If it's 25 gigabyte RDMA, you must plug in 25 gigabyte interface or small form pluggables, SFPs, right? Same with these guys, right? But for Smart I/O, you can buy 32 gigabyte, but you can run 16 gigabyte. It's up to you. Same
so it means each port has a different. For example, for P0, we insert for SFP for fiber channel, and then P1 we can insert for Ethernet. Okay.
But it's not. It doesn't work that way anymore. Last time, yes, but now it's you buy either fiber channel module or Ethernet.
Okay.
So it's just the different sizes of Ethernet. So this guy can be 10, this guy can be 1 gig, this guy can be 25, like that.
Yeah. Okay.
Last time, yes. Now, yeah, for some, I think they had issues with the old Smart I/O module, so they changed it.
Okay.
No worries. And then you have our good friend PCIe. So PCIe Peripheral Component Interconnect Express. You have the 55 gigabyte PCIe module, right? So this is running pure PCIe. This is running InfiniBand PCIe. So if you want to run a 55 gigabyte Ethernet InfiniBand module, you run the InfiniBand module. If you're running PCIe modules, then you run PCIe modules. So depending on whichever version you want to run, PCIe or InfiniBand, up to you, right? InfiniBand, I would say it's more like a transport version. So it's a method of transporting. The actual protocol inside can be IP protocol, can be SCSI protocol, but InfiniBand is just a method of connection. PCIe runs its own sets of protocols and stuff, right? We will cover that later, don't worry. Then we talk about fiber channel and FCOE, fiber channel over Ethernet. So fiber channel modules, you have the base 16 gigabyte fiber channel, right? Fiber channel over Ethernet, you have the 10 gigabyte Ethernet module. So if you want to run FCOE, you have to have the FCOE small form pluggable, plug it inside, and then you run 10 gigabyte Ethernet FCOE. If you have the 10 gigabyte Ethernet fiber, Ethernet module, you can just still plug it in here. So the 10 gigabyte Ethernet module is used for both FCOE and normal 10 gigabyte Ethernet. Generally, a lot of people don't use FCOE anymore. So it's mainly used for Ethernet in that sense, right? But the interface modules are there. Right. So what type of SSDs? What are the types of SSDs? Anyone?
All true.
Or SLC, MLC, TLC, QLC. Which of the following can be used to measure the performance of HDD? Anyone? No?
I think all.
All also. Right? So in summary, we have gone through basically the intelligent storage components. So we started off on controller enclosures. We talked about controllers, coffer disk, backup battery units. We went to talk about disk enclosures. We went to talk about expansion modules, which is the expansion modules and the device cables. Then we talked about the disks, the hard disks and the solid state disks. And finally, we talked about the interface modules. So that is a summary of chapter module 2, chapter 1. Any questions before we call it a close? Cool, no worries.
Yeah, I would like to
No worries,
have some question. Depends on your explanation related to SSD and HDD.
Okay.
So in best practice, if we want to install the server that has a powerful performance, so we have to use SSD, right? And if we want to give a big or give a large storage, then we have to use HDD.
So very debatable.
Yeah.
So if you have application server, right? So first, what kind of application? Is it running database? So some kind of high-powered database or something like that? Let's just
all of them, database and maybe for multimedia purposes.
Okay. Then I would suggest SSDs. I would suggest, I won't say must use. I would suggest using SSDs because application servers are basically facing the customers. So the customer will want to have fast access to their data, right?
Right.
They don't want to have a delay and all these things. So I would suggest in that scenario, use SSDs. But in say like scenarios like you already written the thing into the database, that is the front end SSD. Then later on, you want to do backup and all that stuff for that database, you move it into hard disks. The backup and archiving and all that data you move into hard disk. Make sense?
Yeah. So it's hybrid, right? Maybe or
it's
still full flash storage, or we can say that as a hybrid storage.
So if you're using SSDs and HDDs, that's hybrid storage.
Yeah.
Mhm. But if you're using pure SSDs, then that's all flash storage. Mhm. Yep. So in this scenario, yeah.
In this practice, I prefer to hybrid. Is that right? So
Best practice, prefer everything in flash.
oh, in flash. Oh, okay.
Best
Okay,
practice,
okay.
but
Yeah.
that is best practice. That is
Yeah.
not a
Yeah.
it depend on budget, man.
Yeah. Okay. Yeah. Yeah. That's for sure.
So the budget in the beginning we
Yeah.
plan like, oh yeah, everything must be fast. Then we see the budget, 700,000. Okay, no problem. Let's cut the budget here, cut here, and yeah. So it's all depend on the budget. Everything at the end of the day. So what we'll usually do in that scenario is like this. So you have your server, you have your storage system, and maybe you have a SSD disk array, and you have a SATA or SAS disk array. So this will be SAS, this will be SSDs. Okay, and then you'll have your controller and your server.
Yeah. Okay.
Okay, so when the server talks to the controller for its application, maybe the application is saved into SSDs, right?
Right.
Initially, so it'll all be saved into SSDs and all that stuff. But when you want to do backup of this application, so a backup of all this application data, you move the backup to SAS. Make sense?
Yeah.
So when people are still using the server, or people are using the application, they're still getting the performance from the SSD, right?
Right.
But yeah, for backup and all that, you don't need to worry about performance for backup. Backup is you want to keep your data there. You want to, in case something goes wrong, then yeah, just use SAS or even SATA disks. Doesn't matter, right? So that's the.
Okay.
Hopefully that answers your question, sir.
Yeah. Thanks, sir. Yeah.
Anytime.
Yeah.
So more information can be found here. Sorry. Some recommendations can be found here. And thank you. That will be chapter 2.1. Okay. So the next chapter will be a pretty interesting one, which is RAID technologies. I don't think I can cover this chapter today. Maybe we can cover maybe the basic RAID and stuff, and we'll continue on tomorrow. Don't worry. Okay. So with that said, of course, we take a short break. Okay. So I have to fulfill my 30 minutes break every day, else my boss will kill me, right? So current time is 3:43, or let's say 3:45 for you guys. We will come back at, let's say, 4. Is that all right?
All right.
Okay.
Yes, right.
Cool. Okay, we are back. So now we'll go into module 2, chapter 2, which is RAID technologies. We'll see how far we can cover, no issues. Don't worry, I'll keep it light for today, so I won't go into all the extreme theories and stuff. Now maybe just cover until before RAID 2.0. Okay. Okay. So this is module 2, chapter 2, RAID technologies. So I think we still have a second storage technology trends. Yeah. So we still have common storage protocols, storage architecture, storage network, introduction to Huawei intelligent storage system. I'm guessing we can cover until maybe here, somewhere here tomorrow, and then we'll continue on the next day. So Wednesday, we'll be looking at most likely chapter 3, right? Or module 3. Okay. Thursday, we'll do the lab, and Friday, we'll go into chapter 4 itself. Chapter 5, you kind of have to do the lab to understand chapter 5. So, yeah. All right. Okay, keep going. Cool. So now we'll look into RAID technologies. So this course introduces technologies of traditional RAID and something called RAID 2.0 plus. RAID 2.0 plus is Huawei's block virtualization technology. So this is Huawei's block virtualization, right? So Huawei's block virtualization technology is not actually a traditional RAID. Traditional RAID, there are only a few, and they are bound, let's say, by stone. You cannot change them, right? Block virtualization technology improves on the traditional RAID technology, making it much more powerful, much more reliable in some sense, right?
Which means RAID 2.0 plus is proprietary from Huawei?
Yes, is proprietary of Huawei storage products.
Okay.
So the evolution of RAID technologies aims at data protection and performance improvement. After completing this topic, you will better understand the common RAID levels, the different levels of data protection provided by different RAID levels, working principles of RAID 2.0 plus. We'll spend most of our time here, I guess, and of course talking about dynamic RAID and RAID triple parity or TP, right? So content-wise, we'll go through the traditional RAID, then we go to RAID 2.0 plus, then other RAID technologies. So background. So problems in traditional computer system must be addressed. You have instructions processed per second, so you have CPU 1 million instructions, RAM about 100,000 instructions per second, and then in this suddenly you have less than 300 instructions per second. So these are problems that you face with in the old days, traditional days, right? So this became the system bottleneck of performance. So bottleneck of the disk, because the disk has very little, what you call this, instructions per second. Operations of disk are limited, making it impossible to provide large capacities. Data is stored on individual disks, making it impossible to provide consistent high data reliability. So this is in the old traditional sense, whereby if you are accessing the disk or accessing data on a disk, you access every single disk. So there will be disk 1, maybe you have application 1, and then you have disk 2 for application 2, disk 3 for application 3, and so forth. This is an issue whereby if disk 2 goes down, basically application 2 is not usable anymore. Same for disk 3, same for disk 1 itself. Not only that, because of how that singular disk works, so a singular disk might have instruction process less than 200, right? So maybe 300, 250, 260 instructions per second. 260 instructions per second is not a lot for a computer sequence. You can already see the CPU. CPU can process about 1 million instructions per second. So if there's more instructions coming in, so this is like a funnel, right? So if more instructions coming in, the RAM can do about 100,000, then suddenly you reach the disk, you reach a major bottleneck on the disk. You have so many instructions coming in, but you only can do about less than 300 per second. This, at some times in the old days, leads to a lot of system crashes, system failures, hanging, and all this stuff, right? So to overcome this kind of scenarios, we have RAID. RAID has two major names. So here is redundant array of independent disks. The other name is redundant array of, I'll just change, so of inexpensive disks. Both mean the same thing. They are not a different product or something like that. It's just that some people call it inexpensive disks, some call it independent disks. Doesn't matter, same thing, right? So either way, if they put it out on the internet, or if you go and check some internet documents, suddenly you see it's, hey, why is it called inexpensive disks? It is basically the same thing, right? No difference there. What RAID does is it combines multiple physical disks into one logical disk, right? So if you have like 3 disks, basically you apply some kind of RAID protocol on top of it, and then these 3 disks will become one logical disk, so you have a bigger storage pool, right? Not only that, when data is saved, data can be saved here, here, and here all together at the same time, increasing reliability in some sense. So there are different RAID purposes for their reliability, there are different RAIDs for security, improving performance here and there. So the purpose of basically RAID has multiple purposes. So you can, one purpose is to increase the read and write performance. That is basically catered to one RAID, which has the highest read and write performance. Or you can improve data security, right? So either you go for performance or you go to RAID data security. Depending on the RAID you choose, you will get either one. Implementation wise, there used to be hardware RAID, whereby you buy a RAID card, you apply the RAID card to your server, you slot it in, and then you can run the RAID. Or nowadays, much more people use software RAID. So software RAID is basically you install some kind of software. That software then does the RAID calculations for you. In the old days, people tend to cater more for hardware RAID, because if a hardware card does the RAID for you, you take up less processing power on the storage system and all this stuff, right? Because the hardware card does it, the RAID card. Software RAID, yeah, because you still have to use your CPU and all that for your software RAID. So it tends to take up processing sequence. Nowadays, not so much. Nowadays, the CPU architecture has gone intense. So nowadays, even software RAID comparable to hardware RAID, no difference there. So if you look at it in that perspective, it's much more cheaper to do a software RAID than a hardware RAID, because you just install a software, right? But in the old days, people, or we still see some engineers will still say physical RAID is still better, but that is debatable now. So there are two implementation methods. Either you do hardware or you do software. Either way, it doesn't matter. Of course, if you do hardware RAID, you have to buy a RAID card with the RAIDs that you need. So maybe if your RAID card doesn't have RAID 1, then it can never run RAID 1, right? So you must buy a hardware card with RAID 1 or RAID 0, whichever RAID you want. You must make sure that a hardware card can do those RAIDs. Okay? So that is the concept.
Question, sir.
Yeah, go ahead.
For software RAID, is it running on the firmware or the operating system?
It will be running mostly on the operating system in some sense, so it will take up some processing power.
Okay.
But yeah, hardware RAID, if the like pure new server comes, generally with already a built-in RAID card sometimes. So yeah, depending, multiple ways to do it. But usually we still prefer, on huge servers, we still prefer hardware RAIDs for some reason, right? Still, yeah, we're very skeptical of software RAIDs and stuff. Okay, so what RAID does, basically it combines multiple physical disks into one logical disk. That is the concept of a RAID. Okay, so Basically, if you have multiple physical disks, all have 1 terabyte, you combine them into one RAID group, you have a logical disk of 4 terabytes. Okay, speaking in some sense, but of course, you will see later on some RAIDs work a bit differently. Okay, that is the concept. So for RAIDs to work, we need to understand what we call the data organizational forms. So you have disk stripping. Basically, a space in each disk is divided into multiple strips of a specified size. So usually about like 512 or something like that. Data is also divided into blocks based on strip size when data is being written. So a strip consists of one or more consecutive sectors on a disk, and multiple strips form a stripe. So a stripe consists of multiple strips of the same location or ID on multiple disks in the same array. So basically like this. This is a strip. This is a stripe. Okay, makes sense? So a strip is basically a sector on the disk. A stripe is multiple disks combined to one, or multiple stripes combined to locate one disk. How you understand stripes better? Simple. How many disks you have in the array, that's how many strips you'll have in a stripe. So if you have like in this sequence 3 disks in an array, 3 strips are 1 stripe. Makes sense? So generally speaking, you'll have 3 disks in the array. So 3 strips, so D6, D7, and a strip of D8 will come a stripe of maybe stripe 2. Okay. Then you have the stripe width and the stripe depth. I don't know whether they explain that in the next slide. We'll see. Okay. Stripe width and stripe depth. Stripe depth basically means how big is a strip, right? So if this strip is 512 KB, so basically that's the size 512 KB here, right? Width is basically how long is a stripe and all that stuff. Yeah. So how many stripe width, width equals to how many disks. So the stripe width in here will be 3. The stripe depth is how much files or how much data you can save. So the stripe depth is how big a strip is, right? That they generally just don't ask, but yeah, just giving you more information here. Okay. So these are the data organizational forms. You need to know a stripe, and you need to know the difference between a stripe and a strip. A stripe is basically multiple strips combined together to provide one stripe. Generally, multiple strips of the same location or ID of multiple different disks combined to one to become one stripe. A strip itself is sectors on a disk, physical sectors, right? And that is the concept. Okay. Okay, so strip and stripe, no problem. Now we talk about data protection techniques. Data protection techniques that they use in RAID, they use the AND or what we call the XOR. You can either put it any other way, AND or technique, which we probably learned during high school and stuff. So the AND or calculation is pretty straightforward. Anything same equals 0. Anything different equals 1. So how do you calculate this? Very simple. 1 AND or XOR 1, see 1 and 1 equals 0. 0 XOR or AND or 1 equals 1. 0 AND or 0 equals 0. So if I give you a different number, so like say I give you 101101, right? So how we calculate this? 1 XOR 0 equals 1. 1 AND or XOR 1 equals 0. 0 XOR 1 equals 1. So that's how you calculate what they call the parity. Later on, you'll understand much more about the parity, but the parity is mainly used for data protection. This is the logic. So if you remember, anything same equals 0, anything different equals 1, you're good. And this technique will be used throughout the RAID sequence. Okay. This is how we calculate protection on the disk itself. Okay. Any questions? Cool. Right. So there are different RAID levels for different combinations, for different, let's say, data protection level and also performance level, right? So the first one we'll talk about is RAID 0. This is basically what we call just striping, but no mirroring or no parity. Base data, right? Then we have RAID 1. Basically, we call this the mirror RAID. Then we have RAID 3. Basically, we call this the dedicated parity RAID. Then we have RAID 5, distributed parity. RAID 6, double parity. RAID 10 or nested RAID 10. We don't call it RAID 10 because it's actually a complement of RAID 0 and RAID 1. So RAID 10 is basically what we call a nested RAID, nested mirror RAID, and RAID 50 is what we call nested distributed parity. Okay, so there are individual RAIDs, like RAID 5 is distributed parity, RAID 1 is mirror RAID. But if you do them in a nested sequence, then yeah, nested sequence, that means you're combining two different RAID levels. So here we're combining RAID 0 and RAID 1 and RAID 0. You're combining RAID 5 and RAID 0. Okay, by themselves, they're already RAID levels. However, there are nested RAID levels also. And these are all the common RAIDs or common RAID levels for Huawei. Okay. If you go to like Dell or IBM or somewhere, maybe you'll see RAID 4, RAID 2 or something like that. But for Huawei, this is the common RAID level. So these are what we're going to study. Okay. You don't have to look at RAID 2, you don't have to look at RAID 4, nothing. Just remember RAID 0, 1, 3, 5, 6, 10, and 50. These are the RAIDs we will go through. Each RAID has a different technique. Each RAID provides a different level of protection or performance. Okay. Cool. So let's look at the RAID. So we start off with, let's see here. We start off with RAID 0. RAID 0 is what we call, if you see the term earlier, just a bunch of disks. Okay. JBOD. Just a bunch of disks, meaning when you're putting in data, so you have data of D0, D1, D2, D3, D4, and D5. In RAID 10, minimum you should have 2 disks. So there are some minimums and maximums. So maybe if I have, I don't know whether if I have the chart somewhere here. I think I do, yeah. So if you see in my, basically in my tiny URL or my Google Sheet, you'll see the RAID protection levels there. So later on, you can just use this, copy this somewhere up to you, right? But for now, we'll go through each and every one of the RAID. So RAID 0, minimum, so few things you have to talk. Minimum 2 disks by default. You must have 2 disks to do a RAID 0. How RAID 0 works? So when you're saving data into disks, they save D0 into disk 1, D1 into disk 2, D2 into disk 1, D3 into disk 2, D4 into disk 1, D5 into disk 2. So basically, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. All right. This is what we call just a bunch of disks. Why? Let's say this disk goes down. You can never recover your data. Why? Because the data was split into 2 disks. So if disk 1 goes down, you will never recover your data. In any case, any disk go down in RAID 1 group, the data is lost forever, right? The only way is if you had some backup somewhere else or something, then okay. Else it will just be gone, right? However, Because of how the writing is done, it is the fastest in terms of performance. You have zero level of protection, but you have the highest level of performance in RAID 0. Make sense? The term used for RAID 0 is just a bunch of disks. Striping without error check. So you just stripe, first stripe, second stripe, third stripe, fourth stripe, fifth stripe, sixth stripe. As this disk goes down, everything is lost. Minimum disk, you need 2 disks by default. Okay? So when you write data, yeah, it's like that. When you read data, I think the next one will be read. Is it? Let's double check. Oh. Okay. So when you read data or you write data, it's just same. So when you read data, basically they read D0, D1, D2, D3, D4, D5. It's much more easier to read. They know it just skip one disk, skip one disk, just keep going back and forth. That is RAID 1. Read and write speed, this guy is the fastest. Okay. Protection, 0, nothing, no protection at all. But if you are pure performance, you don't mind your data being lost, RAID 0 is the way to go. Right.
Question, sir.
Yeah.
How about the stripe 0, stripe 1, and stripe 2 purpose for this example?
The purpose for a stripe is just showing you different stripes. So they have 3 stripes here. They're saving data D0 into strip 1, D1 into strip 2. But the stripe performance is basically built on how many disks you have, right? So that is basically going back to this data organizational forms. Make sense? It's how you save data. So when you're saving data, for stripe 0, you're saving like the data might be like this. So data might be 1, 0, 1, 1, 0, 1. Each strip is basically one amount of data. So saving data of D0, you save into D1, D0, 1, 0, 1, 1, 0, 1. So when the application is looking for its data, it just has to know which stripe it is. If you know which stripe, then you know which sector it's located. It's located in sector whatever in D0, located in sector whatever in physical disk 2. Make sense?
Okay. May I make some note in this slide? What if I have another disk in this is this 3? So this is still stripe 0, stripe 1, and stripe 2.
Yeah.
So for this data, we can write this data, the 1 in this, the 0 in this, 0 in this, like that?
Yeah.
Okay. So we cannot do, sorry, I can clear.
You can clear, yeah.
Okay. So we cannot do like this. This one in this, in this one in this one we cannot move in this one. Yeah.
No, that's not how
Okay.
RAID.
Okay. So we must put in the stripe 0 first, and then move to stripe 1 and stripe 2 and so on, like that.
Yes.
Okay. Thank you. Okay, that's clear.
No worries. So that's how the read and basically the write process works. The read process is also straightforward. You read data 0, D1, D2, D3, and so forth. Okay. So it's the fastest RAID, technology out there. However, 0 protection. If anything happens, everything is gone. Okay. Make sense? Cool. Then we move to the next RAID, which is RAID 1. It's what we call mirror RAID. So if you see the data down here, it looks a bit different. Mirror RAID, why they're using a smaller amount of data? Because just to show you guys how mirror RAID works. Basically, you have 2 disks. You make them into a RAID 1 group. So whatever data you save into disk 1, you save into disk 2. Whatever data you save once again into disk 1, you save into disk 2. Disk 1, disk 2. So basically, these 2 disks are a mirror of each other. So they're like looking at the mirror, right? So data here is exactly the same as data here. Data here is exactly the same as data here. And data here is exactly the same as data here. Once again, minimum 2 disks by default. If you want to increase a RAID 1 group, you have to increase it by 2 disks every time. So you can never have a RAID 1 group with 3 disks. Must always be 2, 2, 2, 2. So 2, 4, 6, 8, 10. Always must be even number. Cannot be an odd number. Okay. So that is RAID 1. However, minimum disk is 2. This is something I never talked about. Both these disks, let's say, has 1 terabyte. Okay. You have 2 terabytes. If you use RAID 1, okay. If you use RAID 1, you buy both disks, 1 terabyte, 1 terabyte. Your actual disk space is 1 terabyte. Why? One disk is basically used for mirror. So if you buy like 10 disks, so you have 10 disks in a RAID group, you have 5 disks for like say 10 terabytes, the other 5 disks for 10 terabytes. Your actual space, if you use RAID 1, is 10 terabytes. The other 10 terabytes will basically be used for mirroring. So this is once again cost. So you buy like SSDs. You buy SSDs, 1 terabyte SSD for 200 ringgit or 200, how many thousand ever rupiah and stuff. So you buy it very expensive already. And then you buy 2 of those, but you can only use the space of 1. However, in terms of protection, if one disk goes down, you have a mirror copy of the other disk, right? Make sense?
Yeah. What if
How
we
many maximum disks each side?
Well, usually we don't go above anything above like 4. We'll usually keep it very low at about 1 or 2, or maybe 2, 4, 2, 4, 6 maximum. We try not to go anything above 4 disks or 4 disks in 8 disks in total for RAID 1. Why? Then the writing speed will start getting affected. Make sense?
question, sir? How about we have 2 different size of this? Example, this one 1 terabyte and this 2 terabyte.
You cannot create a RAID 1. Yeah, you basically once the RAID 1 group is created, you only have the lowest amount of disk space. So if first disk is 1 terabyte, second disk is 2 terabyte, it will only come back to 1 terabyte.
Okay, but it's still possible.
In the old days, no. Nowadays, yes.
Okay.
Software RAID possible, but you cannot use the other terabyte of the other disk.
Okay.
Sir, I would like to ask whether it is plausible to have triple redundancy, so triple mirror,
Triple
and whether it will
mirror.
be, and whether it is used beneficial or not.
How do you want to go with triple mirror, man?
For instance, we have 3 physical disks, and the first disk is mirrored to the other 2. So we have double 2 redundancy drives.
Well, in terms of traditional RAID, there is none, but that would just mean, so if you have 3 disks, right? So this is concept, no issues. So you say this is your actual disk.
Yes.
So you have disk D1, D2,
D1 and D0.
D1, D0, right?
Yes.
So that means you're going to buy 3 disks with 1 terabyte each, and you're only going to use 1 terabyte.
Let's say I am a little bit paranoid.
Okay. No worries. Okay.
Thank you.
No issues, sir. No issues. Okay, so let's say if you have that really high demand on what do you call this, disk read and write scenarios, you might want to look at RAID 6. RAID 6 will have double parity, so you can have 2 parity disks. You can have about 2 disk failures. RAID 1 still is 1 disk failure only. Okay, but you don't have a double mirror RAID so far.
Okay.
But of course, there are other technologies that can help you in this kind of situation, like RAID 2.0 and stuff. So your situation will probably be solved by RAID 2.0 plus. But traditional RAID, no, they don't have, let's say, double mirror. It's only single mirror so far. Okay? Does that make sense, sir?
More or less.
Because the technology itself does not, basically they don't have the technology in the RAID. If you want to have that kind of level of protection, you will use some kind of block virtualization technology on top of that. That's why they created the technology. So in terms of protection and stuff, also improving performance and stuff. Like here, you're already taking a big performance hit. So if they actually come out with a RAID technology like this, the double mirror, you are going to lose basically 2 times your storage space, right? So you're buying something for 1 terabyte, I mean, for 3 terabytes, you're only going to get 1 terabyte of storage space. Not only that, your write speed also will be very slow. So when you're writing data, so like a user writes data, so he has to write into this disk first, or the storage system has to write into this disk. So D0, D1, D2. Then he has to write into this disk, and then he has to also write into this disk. So the write process will be very, very slow. Make sense? Now already with RAID 1, the write process is already slow. Because when he writes data here, he writes D0, he has to write D0 again. He writes D1, he has to write D1 again. Same with D2, right? So it will be much more slower on write. Read, no problem. Reading, yeah, D0, D1, can just read from one disk. But writing will be very slow. If you add another mirror on top of that, if the write process, let's say, is 1 second, now you have 2 seconds, right? So it's extra increasing the time there.
Mr. Kevin,
yeah.
Sorry for asking.
No,
maybe I'm too soon to ask about this. On your Google Sheet, maybe you can add another column about the transfer speed or write or read the performance of the speed on your Google Sheet. Maybe you can add so we can so we know the performance of the speed.
Okay.
It's off rate.
Don't worry, I'll add another column here and put a read write.
Yes, as you said that RAID 1 look like more slower than RAID 0. Is that correct?
Definitely slower than RAID 0. For write speed. For read speed,
if we want to know or we want to choose which one of the best practice for our environments, maybe we know, okay, if we use RAID 0 faster, but there is no backup or there is no if we use RAID 1, it's better for the security, but for the performance or speed is lower than RAID 0.
Definitely. So I will edit that later on. I'll put it in there. So don't worry.
Okay. Thank you.
So good question, sir. Yeah, no worries. Yeah. Any other questions? So sorry, sir, but your double mirror RAID, I don't know whether people have thought about it. Maybe somebody has thought about it, but so far they didn't go through with the plan. So we still have only our traditional RAIDs. These are default policies you can find anywhere online, same thing, right? So these are the traditional RAIDs itself. For double mirror, yeah, we have gone until triple parity and all this stuff, but not for double mirror, right? So that is the technology given to us. So there are some reasons why they use it, and this is one of the reasons: read and write speed. So if you have a double mirror RAID, the read speed will be no problem, but the write speed will take a deep hit. So you can see when you're writing data, so how they show it. Do they show how the write works? Oh no, they straight away jump to RAID 3. So when you're writing data, you're basically writing one here, and then you're writing one here. One here, one here. So you're writing, in that sense, 2 times, right? So it takes a bit more longer to write. But reading data, yeah, because it's basically the same data, so reading speed is still the same, right? As RAID 0, RAID 1 reading speed, same thing. But write speed is a bit slower. Okay? Now we're going to talk about what we call, what's this? RAID with, one, is it dual parity or double parity? Oh, sorry. Oh yeah, RAID 3, right? RAID 3. Yeah. Okay, so RAID 0, RAID 1, no issues so far. Now we're talking about RAID 3. RAID 3 is what we call dedicated parity. Okay, dedicated parity RAID. So what happens here? By default, RAID 3 also I give you the minimum. Minimum you need 3 disks. They just use 4 disks here because it makes it easier to understand. Okay, let's take a logical sequence. So let's take a sequence of 9 characters, 1 zeros. So let's say 1 0 1 1. That's 4 0 1 3 3 1 1 1. Okay, so how do you save this data? Okay, so the strip and stripe concept, no issues. So how you'll save the data is you'll write the data 1 0 1 1 0 1 1 1 1. Does that make sense? This is how you write 3 3 3. Okay. All right. After you write the data, then they will build a parity using the XOR mechanism, right? NOR mechanism. So here will be 1, NOR 1 equals 0, NOR 1 equals 1. NOR 1, NOR 0 equals 1, NOR 1 equals 0. 1 0 1, so same thing here, here equals to 1, right? So basically here will be 1. Okay, why is this so powerful? Okay, dedicated parity means that a single disk can fail and you can still rebuild back the disk. How to do that? Let's say this disk dies, right? So this whole disk goes down, no issues. Can you rebuild back this disk? It is possible. So we take the initial numbers. Okay.
So for the parity disk, the last one maybe 0.
The last one is 101, same thing, right?
Yeah.
Oh, yeah, it's 0. Sorry, my bad. My bad. Okay. So if this whole disk goes down, you do a rebuild on the parity. So 1 XOR 1 XOR 1. So this will be 0. And this will be, basically, you come back to 1. Same thing, 0 XOR 1 equals 1, 1 XOR 0 equals 1. So this will be the same thing, I think, so 1. So basically, you rebuild this whole disk, right? And that's how XOR works, or that's how parity works. Make sense? So just by using the parity disk and the current online disks, I can rebuild back the data of the failed disks. So this is how you use parity. Hey, why am I doing this? Yeah. Is it okay with you guys? So if you use this sequence, so you're writing data A, you're writing data A1, A0, A1, A2, then you will build parity 1, right? So you build parity 1. So A0, A1, A2, you build parity 1, B0, B1, B2. Then using the XOR method, you will build parity 2. Then you'll write C0, C1, C2, right? Then you'll build parity 3. Any issues? So remember, you write the data first. So after the data is written, they will check A. So A0, A1, A2, build parity P1. B0, B1, B2, then you do the XOR, build parity P2. C0, XOR, and all this stuff, and you build parity P3. This is what dedicated parity means. Why is it dedicated parity? You have one disk dedicated for the parity. Make sense?
Question, sir. For this write tree, we must choose which one the hard disk we use to parity disk, or it just automatic?
Basically, you'll always take the last disk in the parity. So if you have disk 1, disk 2, disk 3, the disk 3 will be the parity disk.
Okay.
Any other questions? Cool. So that is dedicated, sorry? Oh, okay. So that is dedicated parity. Okay. Dedicated parity is not as used as much anymore because of something called distributed parity, which we'll see next. Distributed parity is the technology or RAID 5 that you always hear about. People always either talk about RAID 0, RAID 1, RAID 5, right? Mainly RAID 0 and RAID 5. RAID 0, because of some data, you just don't care, you just put it in RAID 0, and then maybe later on you do a backup or something, whatever. But generally, you will see RAID 0, RAID 1, RAID 5 used the most. In some situations where you want to have extra security and stuff, RAID 1.0 and RAID 5.0 will be used. Okay, so what is the problem with RAID 3? Write speed, right? When you're writing data, you also have to write the parity. Make sense? So basically, you have to, because you have to write the parity, it is faster than RAID 1, but slower than RAID 0 in terms of writing, in some sense. Okay? Here and there. Because it takes time to build the parity. Actually, it's slower than RAID 1. Yeah. It's slower than RAID 1 in terms of writing. Because RAID 1, you just write the same data twice. You don't have to worry about anything. RAID 3, however, because you have to build the parity, so after you write the data, then you have to calculate the parity. After you write the data, calculate the parity. After you write the data, calculate the parity. Reading, no issues. Okay, reading speed, no issues, but writing speed takes a hit. Okay, make sense? Any questions?
So if the parity disk is failed, so
yeah.
we cannot recover.
If the parity disk fails, as long as your disks are still okay, you can replace the parity disk and then they rebuild the parity.
Okay.
Yeah, but maximum failure of one disk. If 2 disks fail, that's it. So parity only protects a single disk failure in the RAID group. So if this is one RAID 3 group, only one disk can fail in this group and it can still survive. Right? If 2 disks fail in the same group at the same time, your data is lost. Okay? Now we look at RAID 5. RAID 5 is what you call distributed parity. So it's the same concept as RAID 3. However, when you're writing data, so like writing D0, you'll write D1 and you straight away build parity. Then you'll write D2, then you'll write D3 and you will build parity. D4, D5, build parity. So you can see what they mean by distributed parity. Sorry. So basically the parity is built across the 3 disks. Make sense? And this is distributed parity. So this solves the problem whereby single parity disk. Like if you only have like a dedicated parity disk, if the dedicated parity disk fails, you have to rebuild the parity all over again. Here, if a disk fails, you can use the parity of other disks to rebuild the data here. Make sense? So all the disks are taking part in that sense. It is a bit more faster than RAID 3. And it's much more reliable in that sense compared to RAID 3, compared to dedicated parity. Okay? So this technology is generally used by most people. Cool?
Sir, is it hot swappable when one device fail? We just hot swap and they will recovery.
Okay. Only when a disk fails, they will use what they call the. You will always have some spare disks, right? In the device, I mean the storage environment. So let's say a whole storage environment, you have like say RAID array 1, 3, and spare disks. So this is how it'll be. So you'll have like RAID 1, a group of maybe 3 disks here, or 4 disks, right? So RAID 1. Then you have RAID 3. Here you'll have like 3 disks by minimum, right? And then you'll have a hot spare capacity. Maybe a hot spare capacity is like 2 disks, right? So when something is wrong, they will use the hot spare capacity to rebuild the disk, rebuild the RAID. Make sense? So what happens here is, if this goes down, there will be a hot spare disk. So one of these 2 disks will rebuild the RAID. So you'll rebuild whatever comes here. So P0, D3, and D5. Okay. So now you can just run the whole group this way with these 3 guys. Okay.
Okay. So
however, you will have to replace this disk with a new disk. Once you replace this disk with a new disk, they will do what they call a RAID rebuild. So they will rebuild this disk from this disk to this disk. And then this guy will go back into hot spare. Make sense?
okay, so it run automatically.
In usual sense, the storage system will run automatically in the RAID policy. If you have hot spare policy already applied, they will run automatically.
Okay, okay.
Any other questions? Cool. And that is how RAID 5 works. Distributed parity. Okay, that's the main thing. Dedicated parity, distributed parity. RAID 3 dedicated, RAID 5 distributed. Now we look at RAID 6. So RAID 6 is a bit of a topic. RAID 6 is what they call double parity. So you have 2 parities. Minimum disks in RAID 6, 4 by default. You need to have 2 disks, 2 disks for parity. So minimum you must have 4 disks. Okay, 2 disks solely for parity. So you can see here, requires at least n plus 2. N must be more than 2, or more, actually more than equals to 2. Yeah, 4 disks minimum. All right. Also, forgot to talk about these guys. So like for RAID 3 and RAID 5, space wise, let's say you have 3 gigabytes, so 1 gigabyte, 1 gigabyte, 1 gigabyte. Your actual storage space is only 2 gigabytes. So 1 gigabyte is used up for parity, right? Makes sense. 1 disk basically minus 1, right? So whatever disk you have, minus 1, that is the space you have, storage space. RAID 6 is the same. Whatever space you have, minus 2, right? So RAID 6 will start off with 2 plus 2, 4 plus 2, 6 plus 2, 8 plus 2, and so forth. It must always be even number. Okay. So RAID 6, there are 2 different technologies for RAID 6. You have RAID 6 PQ and RAID 6 DP. Do not ask me how RAID 6 PQ works. Nobody knows. Somebody can tell you the configuration, but I do not know how RAID 6 works. RAID 6 PQ works. RAID 6 DP, I can tell you. Why? RAID 6 PQ uses something called the Galois field or something like that. I think it's called Galois field, right? So this is how RAID 6 PQ works. So there's a built-in calculation method whereby you have something called, I forgot who is the calculation. RAID 6 calculation. I think they put it in the slides there, right? Do they tell you who built RAID 6? I know they use Galois field, but the algorithm is not Galois field. Anyways, maybe you can check that out online. So RAID 6 uses something called a Galois field algorithm or GF algorithm, whereby the first RAID is done by parity. So you'll see the orange stuff here. Okay, the orange RAID is done by parity, or the orange disks are done by parity. So that's the normal parity 1010 and all the stuff. However, for the Q part, For the Galois field part, they use something called alpha times D0, beta times D1, gamma, and all that times D2 and so forth. So don't worry, they will never ask you this question in exam. If they do ask you this question in exam, that's some crazy stuff. So to calculate this is not easy, because we need to know the value of D1, we need to know what is alpha, beta, and gamma value. So yeah, so that's only found in RAID 6. You can find it online. So like RAID 6, RAID 6 P plus Q. Okay. Understanding RAID 6. So yeah, how you find A, B, and all that stuff. Go ahead. You can. There are some examples here, but yeah, I don't want to go back into my mathematic days. I basically am very bad with maths. So yeah. But that is RAID 6 PQ. They use some formula to calculate Q and P. P is done by parity. Q is done by some formula called Galois field. So the formula is called GALOIS ELD. I think that's how you spell it, Galois field, right? You can check it out.
With single L, with single L. It's
single L.
With single L. Galois field, single L.
All right. Is it single L? Okay.
Yes. Pretty much. Thanks to cryptography.
Oh, okay. So are you a cryptocurrency trader or something like that, sir?
No. I took cryptography. I took advanced cryptography in my postgrad years.
Oh, okay.
Galois field were drilled so much.
So do you know how this theory works?
Roughly, and it uses some funky maths.
Okay. So we'll just keep it at funky maths. No issues. Right. So yeah, some kind of mathematical algorithm calculation, which I do not know the value of alpha, beta, and gamma and all this stuff. However, if we go to RAID 6 DP, RAID 6 DP is something that we can calculate. Okay. So how RAID 6 DP works? It's double parity. So 2 times the parity check. You have horizontal parity and diagonal parity. Okay. So how do we calculate that? So I think here, even the slide, let me see. Okay. So in the slide, let's say physical disk 1 and physical disk 2 fails. Everything is gone. So how you recalculate the parity? Basically, you will follow the color coded. So you'll do a horizontal parity first. So you'll calculate D2, D7, P2, and DP2. So let's see that again. Okay, so you calculate the horizontal parity to find D12, right? After you found D12, then you calculate the diagonal parity, right? So horizontal, diagonal, horizontal, diagonal, horizontal, diagonal. Make sense? So when you're saving the disks, basically you're saving into one horizontal parity disk and one diagonal parity disk. This is also 2 disks for parity. So that 2 disks are dedicated parity disks. Does it make sense that way, sir? So if you want to do distributed diagonal parity, you have to use RAID 6 PQ. If you want to use dedicated parity, you'll use RAID 6 DP. Okay. Any questions? So you understand this, right? So when 2 disks fail, you calculate the horizontal parity, you get back your value of D12. Then you create the diagonal parity, you get back D13, then horizontal parity, D8, diagonal, horizontal, diagonal, horizontal, diagonal. So when you're saving data, generally you will save data in the horizontal parity first. So you calculate the horizontal parity first, then you calculate diagonal parity later on. So saving data is a bit more longer. Any questions? A bit more easier to absorb this guy compared to the previous PQ stuff. Because maths, not my greatest subject, let's say. That's why I went into IT. Didn't know IT has a lot of maths also. Okay. So that is RAID 6 DP. Any questions? Cool. So do you guys want to stop here, or do you guys okay to continue until we finish all the raids, all the traditional raids? So it's only 2 more raids. Is that all right with you guys?
I'm all right, actually.
I'm sorry, Mr. Breven. Maybe my friends in here, they live in Java. Yeah, so the time is 1 hour slower than my time in Lombok.
Oh, okay.
Yeah.
So for them it's 6 o'clock.
Yeah, I think Lombok is similar as in Kuala Lumpur. I think
So for you it's 5 o'clock. For them it's 6 o'clock, right?
Yeah, and for me now it's 6 p.m. Yeah, almost 6 p.m. Yeah, and
for
I
them
have to prepare for my break, my fast.
Okay.
Yeah.
No worries.
Yeah.
So, yes, sir.
Yeah, but if I want allow me if I might, I want to live a little bit faster than
No issues.
other participants in here. Yeah.
No, I understand, sir.
Yeah.
We are all working adults. So what I'll do is I'll stop here for today. So tomorrow we'll come back. We'll talk about the extra raids and all that stuff. Don't worry, this part will be quite quick, and then we'll move into RAID 2.0. RAID 2.0 will spend a lot of time. Okay.
Okay.
So today we'll stop here. So we stopped at RAID 1.0. Tomorrow we'll come back. We'll continue RAID 1.0, and then yeah. So with that, I would say have a nice day ahead. Stay safe. If you're going out, wear your masks. Practice social distancing, and see you guys tomorrow morning.
Okay.
See you.
Yeah. Thank you very much.
Thank you. See you tomorrow.
Yeah,
Thank you. See you.
Thank you, Bhavin.